Hello and welcome back to this day number 2 of the workshop on P4 programmable switches. This event is organized by the University of South Carolina, ESNet, and the Engagement and Performance Operations Center, and the Great Plains Networks. Today, in day number 2, we have 2 presentations. First, a presentation by the people from International Networks at Indiana, Hans and Brenna, considerations regarding network performance. Then we will have a second presentation by Jun Kim, P4 Campus, followed by a short presentation on Tofino pod for teaching and research, some initiatives that we're doing here at the University of South Carolina. And then we will have 2 hands-on sessions similar to what we had on day number 1. Want to remind you that the lab libraries we are using in this workshop, the introduction to P4 programmable switches using the BMB2 software switch. But there are some other lab libraries, and the ones that are in black, SDN, OVS, NTP, etc. And few others that we will be also developing in the next few months. For example, P4 programmable switches using Tofino, network operating systems, etc. I want to also remind you that all the material has been posted in our website. Last week presentations are in our website. I will copy this URL in the chat window, and we'll be posting also the material that we'll be using today. So at this point, I want to introduce Jason, my co-organizer, and also Jason Suraski from ESNet and James Didon. So Jason, do you want to take from here and introduce the speakers?
Yeah, absolutely. Thank you, Jorge, and thanks everybody for joining today. As Jorge mentioned, the first talk is going to be a little bit more of an overview of some of the lessons that we've learned from the EPIC Performance Engagement Center, as well as some of the work that Hans and Brenna have done in their work for Indiana University International Networks. And we wanted to offer this talk because it is a little bit more of an overview that talks about routing, buffering, switching, and other considerations under the guise of network performance. And this is an important consideration, even when we're talking about doing some of the more advanced features of software-defined networking, because even when we implement some of these advanced features for our campuses and our regional networks and our sites, we need to be concerned about these sorts of things due to the users that are ultimately going to be running on top of them. So I'd like to introduce our 2 speakers here. Hans Ottelman started with Indiana University in the UIT Support Center in 2001 and advanced into a position in the IU Network Operations Center soon after. In 2003, he took a Layer 3 network engineer position with IU Campus Networks. In 2006, he joined the IU Global NOC and built his networking experience in several roles, including network planning and deployment, open flow-based networking, network security, and technical training. He has supported several international projects, including the Man-LAN Exchange Point, the Wix Exchange Point, Transpac, and the Internet to Singapore Exchange. And since 2015, he's worked with the International Networks team at Indiana University and is the network architect for that group. And he is the lead for the EPIC Roadside Assistance Program, where he does a lot of technical workshops and training like this and participates in deep dive workshops. Brenna Mead started out working for the campus networking group at Colorado State University as an undergraduate and graduate student. And she became a network engineer for the University of Denver in Denver, Colorado shortly thereafter. In 2019, she worked for Arapahoe County government as a senior networking engineer, where she designed, implemented, and supported county networks. And Brenna is now a network systems analyst for the international networking team at IU. So both speakers have a lot of experience, and they've structured their talks so that there is going to be room for questions at the end. And we do ask that people use the chat feature to ask questions, and we'll bank them all up and ask them at the end of their talk. So with that, I will turn it over to Hans and Bretta to get us started today. Thank you, guys.
Thanks, Jason. That was a very lovely introduction. So as Jason kind of said, we're just going to take a look at network performance and how things can affect that on research and education networks today. And let me put on. Okay, does everybody see that kind of in the full screen? I can't see the view everyone else has.
Yes, sir.
We're good, Hans.
Awesome. So I'm going to take the first half of this talk and then pass it over to Brenna. So let's get started. A little bit of an agenda here. We're going to talk real briefly about what EPIC is. And then we're going to look at what the difference is between R&E networks and commodity networks. We're going to look at how you might be able to identify performance issues, what can affect your network performance. Oh, excuse me. BGP routing steering mechanisms. We find a lot of issues are routing issues, stale routers, stale routing configurations and things like that. And then Brenna's going to talk also about the routing working group that started this year and how you can get involved in that if interested. So the Engagement Performance Operations Center started a couple of years ago. It's a joint project between Indiana and ESNet. Jason Zarowski is one of the co-PIs along with Dave Gent and Jennifer Schupp. It is a part of the CC STAR program that I'm sure many of you are familiar with, and we're here to support science. It says domestic science, but because the EPIC team is also the international networks at IU team, we will support science wherever, all over the world. And one of our big things is creating partnerships inside the community, whether it be with regional networks, infrastructure providers, science communities that span all the different funding sources. So why do we need an engagement operations center? Today's science is collaborative science, right? A huge example, I'm sure all of you know, is the Large Hadron Collider over in France and Switzerland. The ring kind of spans both countries. Anyways, they're producing not gigabytes, but terabytes of data every day, and scientists all over the world want to look at that. So you're not just producing science in one spot and using researchers in that same spot. You're sharing that science all over the world, whether it be astronomy, or astrophysics or whatever it may be, or high energy physics. So we found that there are sometimes some impediments, whether it be routing or all kinds of things as part of EPIC that causes trouble for these scientists to collaborate. And the faster they can get their science between each other, the better it all is in the end. So moving on quickly here, the difference between a research and education network and a commodity network. My colleague Eli Dart actually made this. The research and education networks is this stuff in the red circle here. It's a subset of the much larger internet, of course. These networks are built for and by research organizations to support mostly their science and research activities. They are generally directly connected together, trying to keep the commodity internet that's maybe built for other purposes, business purposes, out of the middle of the connections. And these networks are built to support high performance science applications while, I said before, the commodity internet's built for other things, right? We'll have large flows usually on the research and education network where, on the commodity network, it's a bunch of smaller or mice flows, Netflix, email, things like that. So I kind of hit on some of this, right? So the research and education networks, we have lots of bandwidth, or we try to have lots of bandwidth available for use. We have a lot of really smart network engineers looking at that and trying to keep that very performant. We try to make deterministic behavior in our routing tables, or we hope we do, to keep the traffic where it belongs and keep the traffic on possibly the fastest paths. And also the R&E community, right? A lot of us know each other. A lot of us are friends. We talk and can work on these problems, end to end. Commodity networks might have all sorts of firewalls and traffic shaping. ESNet has seen, in some of their testing, they've seen high performance flows going across commodity network actually be taken down by a DOS protector. The commodity networks actually saw it as a denial of service and stopped it. And so that's probably not a good thing. And quite honestly, we don't know the architecture, right? We don't really know what kind of devices we're passing through. And on the R&E networks, it's a much smaller subset of the internet, and we can have a little more control over it. And right there, R&E networks are engineered to support science. And of course, keep the science traffic on the science networks. So real quick, I wanted to show this example, and this happened just last year. There was people at the Ohio Supercomputing Center had installed a PerfSonar node, and they were testing that new PerfSonar node on their network to an ESNet host. I believe it was across the country, somewhere on the West Coast. And they noticed here in one direction, they were getting darn near 10 gigabits per second, right? This is a 10 gig host. They were doing really great. But in the other direction, they were doing absolutely nothing, right? The performance was just darn near zero. Oops. And so anyways, Epic started working with the ESNet engineers and the OSC engineers, and we found a couple issues. We found actually that there was a memory allocation issue on OSC's border router, keeping the table from fully populating. So they never actually had an R&E address for the ESNet network pop into their table. And you can actually see this in a clip of the trace route here. It was hitting the Hurricane Electric network on its way to ESNet. And also at the same time, ESNet found an out-of-date routing config as well, allowing for routing asymmetry, basically. And we could see, that the performance was terrible in the direction that it was hitting Hurricane Electric, and nothing against Hurricane Electric. It just shows that the research and education networks are sometimes built better and for these kind of use cases. And of course, they made these changes. They fixed up, I think they had to install a new version of code at OSC on whatever their border router was. But in the end, when they got the traffic flowing across the research and education network, traffic or tests in both directions hit almost 10 gigabits per second, or the theoretical maximum of the network card. And this, of course, also is another example of the need for the routing working group that we'll talk about later, for people to discuss how best to keep their traffic on the R&E networks. So, identifying hard failures versus soft failures. So a hard failure, a fiber cut, power failure takes down a router, your hardware just stops working, whatever it may be. That's something that a NOC, your network operations center, is going to get alerted to. Something, is going to turn red on their screen, and they'll page the engineers, or, maybe your SNMP traps or whatever else notices an interface die. You're going to get a hard down on that. And that's easy to fix, right? You know where that is. You know how to fix it. You just go repair the fiber, you replace the optic, whatever it may be. But a soft failure is different. And they can often go undetected for years. Basic connectivity continues to work, but performance is just poor. And talking a little bit more about that, TCP actually, was built, intentionally designed even, to hide transmission errors, right? So back when they designed it, they were like, okay, there might be packet loss, that's fine. We want to hide that so that people continue to work. Back before we were talking about, having very large science flows. And of course, some soft failures may only affect high bandwidth, long distance flows, and you might not see that in your day-to-day activities. You might never even know there's an issue until someone tries to do this and comes says, hey, I'm only getting 20 megabits per second to wherever I'm trying to get to. So, and then of course, with these soft failures, one network problem can often mask many others. So real quick, active versus passive monitoring. The active monitoring is kind of the stuff that gets you those hard failures, your SNMP polling, your net flow, your logs, you can see that kind of thing there. But active monitoring, the one that in the R&E community we're very used to is perf sonar. And that will help you find some of these soft failures, right? So, I was a campus guy for a lot of years, and I'd be like, hey, wait a minute, people are complaining of this long distance file transfer having problems, and I'd check my network and say, oh, my network looks fine. I'd wash my hands and close the ticket and pass it on to someone else. But then I soon realized that between two endpoints, there could be 5 or 6 networks, even in the R&E network, maybe 3 or 4 different networks. And that there could be a problem anywhere along this entire path, right? There could be something congested at the other end that I can't see from my campus with regular monitoring. There might be a congested link between 2 domains, or more than often than not, maybe, inside a small round trip time, TCP is good enough that it kind of hides it. Maybe between 2 switches on the same campus or 2 devices on the same campus, I can get, near line rate, but it starts to not be so good when you go further out. And this kind of illustrates that a little bit more. Maybe there's a switch with small buffers and it's just having trouble passing all that traffic and keeping its buffers empty. So anyways, one of the ways we like to really take a look at our networks and make sure they're staying clean and tell us when perhaps they drop below a certain threshold is by using perf sonar. We've noticed that consistent behavior does require a clean path, and keeping that path clean amongst many different networks, many of them that you might not control as a campus network engineer or a regional network engineer, you need a tool, and perf sonar lets us see those issues, say between 2 points, like a collaborator and our lab or science DMZ, between 2 science DMZs. It can let you see if there's issues over time. And of course, if the problem is not with your stuff, you kind of do need to be able to prove it, right? So with multiple perf sonar networks, you can work your way through your network and many other networks to kind of narrow down that problem. And of course, my favorite part of perf sonar and the thing we use most in the Epic world, helping troubleshoot things, is the ad hoc testing that I can do to help people prove out a network issue. So I talked a bit about network performance, and let's look at some of the things now that actually do affect network performance. Packet loss, this is the biggest one, and like I said before, maybe in a on a campus, you're not going to see packet loss causing much of a problem because in such a small distance between two switches or 2 servers or whatever, TCP is going to be able to, push through that packet loss. But as you can see from this diagram, as you go out past 10 milliseconds of distance from you, even the tiniest bit of packet loss, 1 out of 22,000 packets, can tank your performance very badly. And these are just the different kinds of TCP that's out there. And then, of course, you can see with no packet loss, the purple line here, it goes down, but not like it does when you have even that tiny bit of packet loss. So talking about packet loss example, this one was kind of interesting. I just wanted to show an example of this. CCNY and Cayutech are part of this NSF grant called Cosmos. CCNY is in New York and Cayutech is in Japan. And they had set up a GRE tunnel. We're actually working with them to set up VLANs now that will be much faster and more performant. However, at the time, they were seeing 0.08% packet loss, and that was just tanking compared to one direction, 80 megabits per second, which doesn't sound like a lot, but this was between 2 GRE tunneled hosts that weren't very performant. But you can see the major difference here with even just that little bit of packet loss. The interesting thing, though, that it was TCP only. When we were doing some UDP testing, it was just fine in both directions. So I talked about perf sonar. We started using perf sonar at different points of the network along the entire path, and you can kind of see where we tested these, and did some ad hoc testing to try to whittle down where this problem was actually happening. So we used 4 different nodes, thanks to APAN and Internet 2 and NEAR and Transpac, of course, for having open nodes. We really appreciate that. So testing all the way to New York, where the NEAR perf sonar node is, from Japan, we saw no problems at all. So we started pushing down into the campus, and we engaged with NYSERNet, the New York regional network, and they actually were the ones that feed CCNY's network directly. And just so happens they were able to put a perf sonar node on the switch, the same switch that feeds CCNY. And from there, we were able to do a lot more testing directly into their campus. And we found a good bit of packet fragmentation and MTU issues ingress. And then we took this information, proving where the problem was. We took the information to the campus engineers at CCNY, and they were able to find a security device, a security appliance that was old and seemed to be the cause of this problem. And luckily for us and for everyone involved, this device was scheduled for replacement. They were lucky enough to be able to get that device in quickly, replaced. And then, the packet loss went away once we got that out of the way, and we are back to what they were hoping for in throughput. So, just even a tiny bit of packet loss there practically can cause some serious problems. So we, talking about switches and route buffers and things, ESNet did this really interesting test, and I've got a couple slides on this, a few years ago, where they would take and looked at these different devices. They would do 30-second tests with 50 millisecond of simulated round trip time, and they would add 2 gigabits per second of UDP background traffic to see what the switch buffers, what each switch's buffers were able to handle. And as you can see, all these different manufacturers handled that very differently, right? Some were much more performant than others. The Brocade was interesting because they were able actually to change the max queue size of the buffer on the fly. And you can see how big a change that was from their 1 meg default on the switch all the way up to 64 meg. And then this is kind of that a better picture of that test and how they made it happen. But also they started messing with the different buffer sizes. I believe this was the Brocade, where they could actually manipulate that buffer size on the fly through configuration. And they noticed that, there's a sweet spot of about 60 megabits per second, right? So it's interesting. And this is something you really want to look at when you're building performant networks or messing with switches, to make sure that they have the buffer in them that they need. Also, you need to make sure you have enough memory on your host, right? And to talk about the bandwidth delay product for a second, with TCP, you have to, you send a burst of data and your computer will wait for, hey, yeah, I got it. You are able to increase that TCP window, and you can see that here. This is one stream, takes 125 megabytes of host memory on the source end to put 10 gigabits a second, 100 milliseconds away. And that's just one stream. So 125 bytes, excuse me, doesn't sound like a lot, but if you have 10, 20, 30 streams all going at once, that starts to increase. So it's definitely something you want to think about, and something we have seen in practice happening, where the hosts were not tuned properly with that window. And when we were able to manipulate that window, the speeds would increase drastically. And Brenna, I think this is where you take over.
It is. Thank you, Hans. So the next network performance issue we're going to talk about is MTU, maximum transmission unit. So some of the ways that MTU can affect performance are mismatches between networks and internal to networks, non-standard MTU changes made or required by commercial providers or DDoS scrubbing services, and path MTU discovery blocked by security appliances and ACLs. Epic wrote a quick guide about MTU, so you can find on this link for those of you that look at the slides later. But we're also going to go over an example that we saw through our Epic engagements. Next. So in order to start troubleshooting, we often look at trace routes. So to begin, we looked at a trace route for an issue between ESNet and NRAO. So as you can see, this trace route, if we had seen the other side, we did not indicate asymmetrical routing. So we had to do a little bit more digging. Often the next thing we look at is MTU. As you can see, this trace route looks fine. So the next tool we used was trace path to see where the MTU changes. Next.
Apologies, having trouble with the keyboard.
That's okay. So initially we did a trace path using 1509 bytes. And if you notice here, after the 8th hop, we get a no reply, indicating that the device that is the next hop cannot handle this 1509 bytes. So in our next attempt, we went down to 1508. And as you can see from this trace path, that was able to continue. So that for us indicated a MTU mismatch between the Maria router and the UVA router. So it wasn't actually an issue with ESNet or NRAO. It was actually an issue in the middle between UVA and Maria. So we were able to locate the problem based on these trace routes and trace paths. So the issue between the Maria and the UVA router, the Maria interface was actually configured for MTU 9192, which is pretty common, MTU 9000. And the UVA interface was configured to MTU 1518. And that's why we saw that difference between the 1509 bytes and the 1508 bytes that indicated this MTU problem. So with path MTU broken, there was no hope for the external MTU 9000 equipment to negotiate appropriately with the appropriate MTU with the NRAO node. So in order to fix this, we actually had UVA change the MTU on their router interface to match that of Maria. But then they were still able to keep their downstream equipment on the campus at the standard 1500 that was their standard throughout their campus. So we only had to make this one change and it impacted performance dramatically. The next type of network performance issue we're going to go over is asymmetric routing. Hans touched a lot on asymmetric routing in some of his examples, but I'm just going to touch on one more. So transfer performance can be impacted by asymmetric routing. It can reduce flow throughput. Large latency differences can cause problems between the two routes, and then round trip time impacts performance. So if one side has a shorter round trip time, the performance is traditionally better. So this is an example that actually came out of the routing working group, which I will talk about at the end of this presentation. But we noticed that there was internal to Asia traffic traversing the US. So I didn't include the trace routes, but I did include the institutions that we saw the traffic going through. So Singapore to Taiwan was using Singaren, APAN, LL, ASGCnet, which is the Academica Sinica Grid Computing Center in Taiwan. So that traffic stayed internal to Asia, and our persona results were fairly good. We saw 2.6 or about 2 gigs per second of traffic consistently on those links. So on the flip side, Taiwan to Singapore, as you can see here, it takes a completely different route. So it starts in ASGCnet, then goes to the US, Chicago, transversing Internet 2, and then over to LA, and then over to Singaren. So the performance on this side of the route was was much worse, about half, so 815 megabits per second. So once we were able to fix this asymmetrical routing, and all it really required was some BGP pairing changes, was the round trip time dropped from 290 milliseconds to approximately 49 milliseconds on that Taiwan to Singapore route. And we were able to see consistent performance from Taiwan to Singapore now in between 1.5 gigabits per second and 2 in each direction. So as you can see from this example, asymmetric routing, especially the longer distances you go, can have a huge effect on your performance and what you expect the performance to be. So these are something that we keep an eye on. This is an example of an issue with BGP AS path. So BGP is going to try to pick the shortest AS path. And if you look at this diagram, technically, the shorter AS path is using the commodity provider. However, as Hans sort of touched on earlier in his presentation, the commodity provider not only has smaller pipes, so as you can see there, that's only a 10 gig pipe. They also don't have the configurations for research and education networks. So though it seems like BGP should pick the AS path that is 3 because it is shorter, it seems like the better path. In reality, the better path is the regional networks, the RNE networks, AS path like 5. So these are things you need to look out for as network engineers as you're configuring your BGP. And as many of us know, BGP needs care and feeding. BGP just works in many cases, but in order to be tuned for performance, you need to pay attention to how it's actually acting versus how you think it's going to act. Best path selection is a 10-step process. As you can see from this diagram on the right, this is how Cisco BGP best path selection occurs. Some common steering mechanisms for best path selection are local pref communities, AS padding, and MEDs, which I will go over in the next few slides. Local preference. So this is based on your prefix. The higher path is preferred. This is a good tool for keeping RNE traffic on RNE networks. So you set your local preference to the higher preference so that it will use RNE networks instead of the commodity, as sort of illustrated in this diagram to the right. This is a fairly simple way, and it does work in many cases correctly. Something that a lot of people in the RNE community are moving towards, especially Internet 2, et cetera, is community strings. You can make changes to your routing policy based on per prefix strings. So the prefixes can have multiple community strings. This can provide pretty useful information about your prefixes, and communities that might be useful to external networks should be made public. So as you can see in my next slide, Internet 2 actually did this with their network. So these are the BGP community strings offered by Internet 2. So when you look at them, you can sort of make assumptions based on what you're seeing in the community string. So you set your local preference on your advertised prefix. So default's 100. And then as you can see, for that ASN, we have 40 is the low and 160 is the high. So notice that's the 160 is above the default and the 40 is below the 100. So some prefix identification. So for this ASN, the 5004 is Amazon. Where does the prefix enter your network? That 242 indicates New York. That 911 is an emergency. Discard all the traffic destined to that ASN or that prefix. And then AS path padding. So you can prepend it to ×1 to create an AS path padding. AS path padding. So BGP will choose the shortest AS path. So you can add one or more copies of your ASN to the prefix advertised to specific neighbors to create this AS path padding. As you can see in this example here, there's 3, 133, 465. So that's an example of AS path padding.
This one's kind of a hammer, and we've seen some craziness out there where people will pad 5, 6, even 10 times to try to steer traffic. And if you're padding that much, there's probably a bigger issue at play that we need to address that's not, but this can be a quick tool to steer traffic for sure.
Okay, so we went through all of these network performance issues. We showed all of these examples, but what does it mean? What is the takeaway? It's important to realize that routing does not take care of itself. BGP is great, but as we touched on, sometimes it doesn't do what you think it's going to do. Old routes may not work well with the new networks that come up. New routes may come up and not work as you thought or work as you planned. So how are we addressing this as a community, specifically as an R&E community? And that's where the routing working group comes in. So the routing working group, what are our goals? So initially we have an engineering focus, obviously, because this is a group of network engineers trying to solve routing problems throughout the world. So from an engineering focus, we want to document possible erroneous routes or anomalies in our routing, identify teams to address them, and then check in together as a community as we work through them to make sure that, again, BGP is acting the way we want it to, that the changes we are making are actually having positive impacts throughout the community and in terms of our engineering and our networks. And again, also we want a policy focus. So we want to create some better, more detailed and better routing policies for these paths, including preferred backup paths. And we also want to verify that this policy is actually being followed. Again, because what we think happens in networks isn't always what happens. So the routing working group has seen quite a few of these things that we touched on. So some of the topics that the routing working group has tackled in the past year that we've been started. I am the co-chair of the routing working group along with Hans Adelman, my co-presenter for this. So some things that we've seen, as I touched on earlier, asymmetrical routing, the example I touched on came out of the routing working group. Also, R&E data taking a less efficient route around the world, as we saw with my example. For another example, so Europe to Asia routes traversing the US, or Africa to Europe routes traversing the US. Another example we touched on, R&E data taking a commodity route when an R&E path is available. Again, commodity routes tend to have performance issues, and an R&E path is usually the best path for that R&E data. New R&E links are removed or added, but routing does not adjust appropriately. We saw this with the Singapore to Guam link that just came up. We went through an exercise of confirming that as those links came up, the routing adjusted appropriately in the way that we thought it would. Leaking of private ASNs into the global routing table by R&E networks, and then IP blocks advertised with a bogon origin ASNs within the R&E routing table. So these are just a few of the topics that we've been able to address in the first 9 months, essentially, of this group. So this group does work based on cases. So the co-chairs, Hans and I, take your cases in, and we develop teams to address these cases. So if you have a case that you've heard of or seen in your network or someone else's network that you would like addressed as part of the routing working group, feel free to contact us. Our emails are there, mine and Hans, and then we have a third co-chair, Warwick Mitchell. We also have a routing working group email and email list so that we can contact everyone through that group. We also have a Slack instance and a website. We have over 151 members of the routing working group as of right now. And we're always looking for more cases and more members of the community to join us. Contact any of us for more information. And then finally, for those of you who were interested in more information about EPIC or any of the topics that we addressed today in this presentation, feel free to contact epic@iu.edu or go to our website or contact Jen or Jason directly. And I believe that may be the end of our presentation.
That is.
Well, thank you very much, Rin and Hans, for this great presentation. So if you have any question, feel free to write in the chat window or unmute yourself. Let's wait in case there is any questions. Brennan, Hans, I have a question. When you were showing these issues over long distance links, I'm curious if the different flavor of congestion control algorithm can mitigate this problem, like BBR, for example. Did you have the chance to try different or try to fix by using different congestion controls?
Let me pull that back up here. It actually, if we go back to the packet loss screen, somewhere here. So yeah, this was done a few years ago. So yeah, it does show, you know, honestly, Reno, HTCP, and yeah, are all kind of having the same problem. Although BBR is huge, and I know Jason actually may be able to speak to some of the work ESNet's been doing with BBR, but it seems really promising in this space. You know, packet loss still causes issues, but nowhere near the way it does with the older TCP algorithms. And BBR version 2, I believe, just came out, and I know some of the guys at ESNet that I work with are very excited about it. So,
thank you. Well, thank you again, Hans and Brenna. Thank you very much for this presentation. And we'll be posting this presentation on our website. Now, I want to introduce the speaker for the next talk. We have a talk that is by Jun Kim from Princeton University. The talk is P4 Campus. Jun Kim is an associate research scholar in the computer science department at Princeton University. His current research focuses on building better network systems, applications, and tools with software-defined networking, programmable data plane, and P4. He's also enthusiastic about deploying such system in a real network. To this end, he's also the cyberinfrastructure engineer in the IT department at Princeton University. His high goal is to make computer networks easier to monitor, understand, secure, and configure. He received his PhD and master's degree in computer science from Georgia Tech under the supervision of Dr. Nick Finster, and his bachelor's degree in computer science from the University of Wisconsin at Madison. He did several research internships at HP Labs in Palo Alto. He also worked as a software engineer in South Korea before graduate school for several years. Jun, thank you for being here. I would let you share your screen right now.
Oh, thank you. Thank you so much for the introduction. All right, let me try to share my screen. Is that working?
Yes, this is working.
All right, so thank you everyone for joining. My name is Jun Kim from Princeton, and today I'll talk about the Princeton P4 campus. It's about building and running novel network applications on campus. So I'll start with the definition of P4 campus. It's basically an initiative to create and deploy experimental but useful network applications on a production campus network. And because we primarily use programmable data planes and P4, we call it P4 campus. And this talk is basically about why we do this and how we do it. And so starting with the why, we all know there is a huge gap between the research and production network. Let's say you have a really good idea, a new idea, but mostly we just work on small, very unrealistic experiments. And then it never actually gets to the production network. Whereas the production network is getting more and more complex, but the operators and network practitioners are still stuck with very outdated tools and practices. There's also a bigger problem that someone might come up with a really bad idea, right? Like electric drill with a manual screwdriver attached to it. But because it also only runs on small and realistic experiments, it stays as a bad idea. So that's the whole problem for us. So basically, we're missing this positive feedback loop between research and production network. So to elaborate on this a bit more, to me, I think the network research pipeline kind of looks like this, where you start with an idea and design, right? And then people work on softwares and simulations, network simulation emulations like MiniNet or NS2, NS3, NS3 or something. And then hardwares can come along, and then you will actually run some experiment with hardware and that's synthetic traffic. The next stage would be actually doing it with real traces, and ultimately you want to have a real deployment with live traffic. And the important part is that every step has a feedback loop to the idea and design to make it better. Most of the time we are missing all these three stages, but luckily, these times we do have the hardware, and these are programmable hardware, P4, some other stuff that makes us actually run our experiments on real hardware. But we are mostly all still stuck with synthetic traffic. And without these two stages of real traces and real deployments with live traffic, new ideas will barely see the light outside of the lab. So this is basically kind of like the motivation of the P4 campus. But here, the thing is about real traces and deployment, it's basically very hard to do, right? Because let's say you ask the operator, like, I don't know, put some programmable switch in your network, they're gonna say no, because it's disruptive, right? And then there's all things about user privacy in the real traffic. There's personally identifiable information, and also there's generally a lack of collaboration between and communication between the IT department and the research community. So it's really hard to get these last two stages. The community did come up with really good alternatives as well, like dedicated test beds. There was Planet Lab, there was Genie, and more recently the Fabric push and effort. These are really good because they're real networks and they're WAN scale, they're really big. But they do essentially have some limited access to the production traffic. I think Fabric is in a much better position right now because people are thinking about this and it's going to have a connection to the internet, all that stuff. But definitely the past two dedicated test beds had some limitations here. And if you think about the campus network, it's actually a very good lab. So campus network as a lab, because there's a variety of traffic you can see on the campus. There's science traffic, there are data centers. If you have dorms, there's residential traffic. And running a campus is business. So there's a business traffic as well. Another good thing about campus network is it's open and dynamic. So it's generally open to the public. There's a lot of visitor Wi-Fi access going on. A lot of visitors come in, there are a lot of events going on. People bring their own device to the campus, and the network itself is very close to user too. Some people say, every services, enterprise services is just moving to cloud. What does it make sense to monitor a campus or enterprise network? But it still has a value as an access network, and enterprise solutions are still applicable to cloud network as well. Another good thing about campus network is that, first of all, it's research friendly. And this is a website, if you just go to the IT department campus network, it says enabling research. So, campus network wants to promote research, right? And then there are existing mechanisms to help you do that. There's IRB process. Princeton has this another thing about requesting data for research process. So the campus and educational systems tries to help you do better research as well. So this talk is basically about how to jump this research chasm from research idea to real campus deployment and get those two last stages. Jumping over the hoops of just being disruptive and privacy issues and lack of collaboration. So this talk will be about sharing the experience we had, how to be less disruptive, how to preserve the privacy, and how to promote more collaboration with the IT department. And also we'll share some successful deployments we had with our P4 apps. We have developed it and actually run against real traces and traffic on our campus. And I'll talk about the 3 of them. We have a bunch, and I just cited some here, but there's a lot more. But for the time's sake, I'll only talk about 3 of them briefly. So let's start with the first thing, being less disruptive, becoming less disruptive. And basically, it's about working with mirror traffic, and then starting with passive monitoring apps as a gateway drug for people. I mean like IT departments as well. So what it means to be doing traffic mirroring is basically, this is a very crude and high level topology of the Princeton network. We have 2 routing paths to New York City and Philly, 2 border routers and 2 firewalls and 2 cores and buildings attached to the cores. The thing about this is like our networking IT department team deployed a lot of network taps, which is basically a small device that goes in between links and makes a copy, a mirror of the traffic that is passing that link, right? And we deployed a lot of them around the campus, mainly for monitoring and whether we want to do monitoring right now or some forensic analysis later or debug a problem like that. And a lot of campuses actually do this. So what we have at Princeton is there's a lot of tap devices deployed around our campus network, and they are mirroring live traffic to a packet broker system. And the packet broker system can apply some filtering, and then forward it to some some destinations you want. And our department team is actually forwarding a lot of traffic to their own analysis tools to figure out what's happening on the network, whether it's monitoring, all that stuff. And what we basically asked was, oh, you already have this, and which is very common in other campus networks as well, is can we get a sleeve of that packet broker system so that we can also forward it to our P4 switch, right? And then we'll install some apps on our P4 switch, and bam, then you have real traces coming to our P4 switches, and we can test our apps like that. And actually, this was not at a hard of a, I mean, there were some hoops we had to talk with the IT department, and I'll talk about the privacy issues later, but this was actually not that much work for the IT department to begin with, because they already had that infrastructure, right? So working with mirror traffic is awesome because basically it's very low risk because it's little or no disruption to the network. You're not actually in the path, you're just getting the mirroring of traffic and like analyzing that. And there's a very high return because you can do real-time traffic analysis. And it's a very good way to convince your IT department as well that you can help if you can do better analysis for free. Some tips about mirror traffic is, well, they call it tap devices or test access points. It's much better than port mirroring. So port mirroring is another thing. I think it's they call it span ports. Sometimes you hear, there's a thing on a switch or router that you can turn on, like you want to turn on a span port so that you can capture some traffic and send it somewhere. Tap is much better than that because it's a dedicated device outside of the switch, and it doesn't use the resources on the switch. So spam will burn a port on the switch and also resources on a switch. So it's not always tap is much better. And there's a lot of variety of modern packet broker systems out there. They can do filtering. They can remove or mask the payload. They can remove duplicate packets if there's a duplicate going on the link, or if you tapped several places along the path, but you don't want to see them happening twice. There's a lot of good packet broker systems out there which you can also look into or figure out if your department is having that or not. All right, so the next part is about preserving the user privacy. And there's two things here. It's about IRB and then data anonymization. So how to navigate the campus traffic data access. As a researcher, there's two things. First of all is institutional review board, which is about rights and privacy, welfare of human subjects. And you might think like, why is network traffic, a welfare of human subjects? But it's basically about privacy, and you have to really take care about this aspect when you're doing research. Another thing is patter, which is not sometimes present in some campuses, but Princeton does have it. I do know some campuses are having this or some similar thing. It's more about using the administrative data for research. And it's more about the welfare of the university. Like, can we share this data? Is it gonna harm us some way? Is there any security? Is there any feasibility issues? Is there any risk or compliance issues? Are we gonna get in trouble because we shared this? So they have a whole nother body for the university about reviewing the use of data. So it's good to know whether your university or campus or institute or enterprise has this kind of thing, and always check with them if you have to also clear that bar as well. All right, so because that's very specific to Princeton, let me talk about the RRB more. So when you're prepping your RRB, like you have to do a RRB before you're gonna play with the real traffic. That's almost a must. So when you're preparing your RRB applications, always try to state that you will remove or anonymize all the PII. And MAC and IP address is just some examples of that. There could be more. You want to say you want to remove all the payloads, of course. Although a lot of stuff are encrypted these days, but it's better to just remove the payload. And if you're not able to do that, you will probably you should state that the operator will run or scripts or programs for you and only give you aggregated results so that you don't see any PII when you're looking at the traffic. And also another good thing always is to say that you're gonna take good care of that data. The data you will be storing and processing will be at the machine managed by an IT staff, not your personal machine, not your personal laptop. You're gonna not take that data to home and or copy and send it to someone else. Always say that this data will stay in a very secure place managed by a professional staff. So what about anonymization? So there's a lot of tools out there, which are probably, many of them are outdated. So, but they're still out there. Some are really good ones. And offline data anonymization, if you go to Kaida, which is a very known place for sharing some traces as well, real traces, one of the few of them, they have some good documentation and writing about how best practices and what tools to use for anonymization, given that you have a trace that has to be anonymized and saved somewhere. So those are good resources. Another one I want to present is a use case or example of P4AB, but also an enabler for our research. And it's called OnTask. And it's about anonymizing live traffic as it comes in. So basically, this program is a P4 program that runs on a programmable switch on a real hardware. And it will, when the traffic comes in as raw, it will actually anonymize relevant fields. And you can configure with the controller which places you want to anonymize. And then the output of that switch is already anonymized traffic. So you don't have to run any after offline tools to anonymize it. You already have an anonymized traffic coming out of the switch in real time and live traffic. So this is hugely useful for us. And so what we basically do is when the mirror traffic comes in, we first have a hop which anonymizes it and then send it to the servers or switches we want, and then do the analysis. So, as researchers mostly are just bound to the P4 server on the right side, so they don't see the raw traffic in the first place anyway. So this is a really good tool for us, which we use a lot. A bit more detail on it, which I don't want to go in too much detail. I mean, you guys, probably the workshop already talked about how to do the parsing. So basically this piece of program is like a packet comes in, this is just the IP header, and you parse it. And there's a hash function. The built-in hash functions like CRC32, you can add a salt. You can also implement your own more secure hash function if you want. And then you take the source and destination IP address, which are raw, and then go through the hash function on the P4 program. And then, you deparse, or making like we make the packet again with the hashed source address and hash destination and an output. So it's basically doing that. And good thing about this is online, meaning it's not offline tool. And offline tools take a long time too. If you think about it, like it takes a long time. You have to feed the traffic, and then you have to all these computations on the server to spit it out. And then there's also a question about how to save that huge data in the first place, right? But the good thing about this is like it's already done when it comes out on the switch. It's line rate and it's customizable because you can select the IPs you want to anonymize. Some IPs you can say like I'm not going to anonymize. You can also do prefix preserving anonymization, meaning like you're going to do /16, like you're only going to hash the last 16 bits or something like that. That's all possible with ONTAS and this program. So it's hugely important for us. And right. So that's basically about the ONTAS program we have. The last part is more collaboration with the OIT department. Of course, you want to tackle problems that matter for them. And then the other thing is having a joint position if possible, which I will talk about in more detail right now. So collaboration with OIT, meaning like, let's say you finally convince them to mirror the traffic and get anonymized traces for your research. And even before that, when you're trying to convince them, you want to say like, I will try to really help you guys too when I get this. Like, it's not a lost cause for you, and we'll do it for free, right? And so you're trying to find problems that really matter for them. I mean, let's say you ask for the help from operators that, give me live traffic and please anonymize it for us too. Then I assure you they will probably not do it for you because that's a lot of time and effort. But let's say like you tell them like, I'll also do the anonymization for you. So that's how actually ONTAS happened. We said like, you don't have to do anything. We'll just put the P4 program. You can review it if you want, and test it if you want, but it does the anonymization for you. So you don't have to do anything, just forward us the weird traffic, right? So that's how ONTAS kind of born to help them so that they can help us better as well. They also had some problems, like we asked them, do you have any problems in the network? They actually reported they have a switch that is dropping packets occasionally. Can you help with that? We actually had a P4 program that would monitor the queues in the switch and pinpoint the flow or packet that is causing the queue to build up. So we had that, and we're able to help them like this particular flow or traffic is causing a lot of problem in that switch and probably making packet drops happening. They also had, IT folks also asked a lot of questions like, do you have any latency problems in the network? We have latency problems, but it's really hard to pinpoint the bottleneck. So another app we had was P4 RTT, which is about continuous RTT monitoring on the passively doing that, not active measurements, but like Persona, but it's more like looking at the traffic passively and trying to figure out the RTT of that flow. And with this, we were able to see like, is the bottleneck is the wired, is the wireless, which I will also show you later in this talk. So you really want to like ask these questions, and if they have these thoughts or like, can you look into this with the traffic you get? And like, it's really good to think about these problems, to ask them and find problems that matter for them as well. And that will really make you build a good relationship with the IT department. Another advice that kind of worked for us is, which might be special, but it's not a crazy idea, is having a joint position. So that's basically me. As you heard in the introduction, I'm a cyber infrastructure engineer in the IT department, but also a research scientist or scholar in the CS department. And actually, at some point, that was the my salary was 50 and 50. So I was shared among these IT departments, CS department. And I did have this joint position, which is sometimes very good because you have a person that can work on research projects, but also has access to campus network. And basically you're the bridge, that person can be the bridge between the research community and the IT department. Because this person is kind of dedicated to help make that connection. So it's not a crazy idea sometimes. Actually, NSF had some funds for this. That's how I started this position. So it's something to really look into. All right, so next I will talk about some successful deployments we had. The first one I want to talk about, the P4 programs I want to talk about is the real-time operating system fingerprinting. The second one is about continuous RTT monitoring, which I hinted just before right now. So P4OF is our P4 research project, which was about fingerprinting OS in the P4 switch. And some people thought, like, why do you want to do this anyway? But the thing about network policies, when you're writing a network policy, you really want higher abstractions than IP addresses sometimes. Like, say, maybe you want to write a policy based on OS types. Like, you want to block all traffic to and from Windows XP machines on the campus because Windows XPs are out of they don't update it anymore there. And maybe you can say, like, you don't want these traffic operating systems talking on the network anymore. Maybe that policy you want to actually apply on the network. You can say rate limit traffic to and from EcoDot because these image and EcoDot shouldn't be using so much traffic. Or you want to say, like, I want to actually monitor the OS distribution. What kind of operating systems do we have on a campus in real time? Like these policies, you can write in high, you want to write in high abstractions. And we believe this kind of work can help you do that. So the idea is that as packet comes in, that, based on the host IP, you'll be able to label that this is a Linux machine. This is a Windows machine right in the switch. So this work is based on the POF tool or POF, but POF, they call it POF. The premise of this work is that each operating system uses a unique combination of TCP and IP TCP header values. And the POF signature is basically a combination of these. Like it's first, is it V6 or V4? Is it using IPv4 or IPv6? And then the initial time to live set on the host. Does the host set IP option lengths, the maximum segment size, and then the TCP window size and scale, and as they start, the TCP option layout. So TCP has this optional option, and what's the order of them if they have any values for that, some quirks, and then some payload classes. So this combination actually is able to become a really good fingerprint of an operating system. That's about the POF tool. And it's a tool that runs in the server, right? If you feed in a PCAP file, it'll try to figure out what's the OS for this source address. And an example of this signature is Linux or 3.11 or higher will have this kind of fingerprint, right? And now if you think about it, like, oh yeah, P4 can actually parse all these headers. Can't we do it in the P4 switches as well? And that's basically it. The POF tool itself cannot run against live traffic with high data rate, right? It's basically an offline tool. So the P4OF work is about doing that in the switch, in the programmable data plane. So how it basically works is like packet comes in, we do the parsing of the TCP IP headers, and then it also parses all the TCP options. And this TCP option layout is a huge fingerprint. It's very unique for each OS. And then the switch kind of collects all this and then save it in a data structure called POF metadata. And then basically before that packet thing is coming, there's a match action table. I think there's going to be a tutorial on this later today, how to do that. But the operator can say, for these POF signatures, I want to label it as Linux 3.1 and then drop it, right? So they can pre-populate this match action table in the P4 switch so that when a packet comes in and it has this, the P4 metadata kind of matches the signature, it'll actually drop right as the packet is entering. and before it actually exits the P4 switch, right? So this is basically how it works. And of course, there's deparsing. If you're just marking the packet to have a label or not, you can also still like let it send out the packet as well. Or maybe the policy was to just pass it through is fine. Then it'll send out the packet. Right, so we actually did implement our P4OF in real hardware and then feed real traffic and against 3-hour campus trace. And this is a result. There are a lot of numbers, but basically the left one is for internal campus hosts and the right one is for external hosts, meaning like the campus, the external host from the campus, so users from the internet. And you can see it basically, the second column is the POF, if you do it offline. P4F is the third column, and they kind of roughly match. Of course, it's not perfect because POF software tool has some other logic going on to figure out, have a better accuracy, but you can see it roughly P4OF is doing a great job on counting the number of Windows and Linux and all the versions, Android, Mac OS. It's surprisingly perfect for Mac OSs. For external, it's a bit harder because there's a lot of more variety of stuff happening on the external network. So but it's still doing a pretty good job, if you can see. One thing you might notice is well, there's a lot of unclassified for both POF and P4OF. That's a very good question if you're thinking about asking that. And the reason is the POF signatures right now are very outdated. So one of the good future works, and someone can also work on it too, is to figure out the more updated, there's a lot of more different OSs out there, but I'm sure they have very, very unique signatures, and to have an updated database for that so that this actually is applicable to the today's traffic. Right, so that's P4OF. The next application I want to talk about is P4RTT. And this work is about passively monitoring the TCP round-trip time beyond the TCP handshake. So this is not just monitoring the SYN and SYN-ACK and ACK. It's more than that. It's more, after that establishment is happening in TCP traffic, there's a bunch of sequence and ACK going on as data is going back and forth, right? And what you basically want to do is do a diff between that sequence and ACK. Based on where the vantage point is, you will be able to actually figure out the continuous round-trip time for this flow until it ends, which is awesome too. It's not just at the start. So P4RTT, how it operates, basically simplified, you have a home network or a campus network, which is going to the internet, and your vantage point is somewhere in the switch. You have a tap traffic coming into the P4 switch. Let's say the external leg is, from the switch to the internet, and the internal leg is switched to the campus host. And the P4RTT program will be running in this program data plane, and a stream of RTT measurements will go to the server or collection or analysis server, which we will do some analysis ourselves. Or basically, you can do some stat monitoring in the switch if you want as well, instead of sending the stream of RTT measurements to a different place. So I want to go a bit more detail in this, how it works, because this program uses another good feature in a program data plane is called registers, which are stateful memories. So you can actually save stuff. It's like a memory, it's stateful memory, right? So what happens is we have a hash table in the register as a hash table. We use it as a hash table. And when the sequence packet comes in, the blue one, let's say A to B, we save that and along with the timestamp. And then we say, and always this comes with the sequence number and the packet size, so you know which kind of ACK should come in. And when that ACK comes in and matches that number with the expected ACK, and the ACK number actually matches, then you will do the diff of the timestamps to get that the time difference between the sequence packet and then the ACK packet from the when the return traffic comes in. So it's basically joining that expected ACK and ACK fields to get that timestamp diff. and all this happening in the data plane. And you can think, well, isn't there a memory limit on the registers in the data plane? Wouldn't there be hash collisions? There's also all these TCP quirks and vagaries of TCP, you know, delayed ACK and all that stuff. Wouldn't it be this challenge? And yes, it is a challenge. So the research project was mainly also about how to use that memory and in the P4 switch more efficiently. And there's multiple different ways to do it, but just to state some of them, it's about also lazy. So the biggest thing about memory is like these TCP stuff is sometimes ACK will never come. That means that you're still occupying that space, which will never be removed because there's no ACK coming in. So another of some technique you can do is to lazily expire that entry. If it's over, let's say like it's been there for over a minute, that entry, that you can probably safely assume there's not going to be an ACK coming in for that. So you can say another entry can safely rewrite that location, right? That's one way of reusing the memory and getting rid of basically garbage collection of things that will never get an ACK later. Another good technique we do is that instead of having one hash table, you'll have a multi-stage hash table. So actually the P4 switch has enough memory to do a multi-stage. So instead of having one big hash table, you can have multiple smaller ones with a different hash function. So when it fails to get into the first stage, you try the second stage with a different hash function. And if it fails, you go to the third one with a different hash function and so on. And actually this performs much better than having a one big register hash table for this. So this is how we kind of get rid of the hash collisions and memory issues when dealing with so many TCP packets. So with this program, what you can do is very interesting stuff. You can actually pinpoint an application. So you can do a per application RTT along the time. For example, if you know the IP address of the YouTube server, you can say, what's the continuous RTT for this YouTube traffic? If you know the IP address of the Netflix, or you're able to identify the Netflix traffic, you can actually monitor just the Netflix traffic. Or Zoom as well. Zoom actually publishes their IP addresses they use for Zoom. You can filter things and then monitor based on their IP addresses above the Zoom traffic RTT going on, which is very important for video conferences like this traffic, right? It's really important that the latency stays well. So this is one way to monitor throughout the connection how things are going passively. Another good application for the IT team, I think what we did was I actually didn't go into much detail, but before RTT is able to measure the external leg and internal leg separately, based on it's really based on the direction of the sequence and ACK, right? So it's a sequence ACK. If the sequence is coming from the internet down to the host, the campus, and the ACK is coming from the host back to the internet, and the vantage point is in the campus, you're actually measuring the internal, right? For the external, the other way around, the secant ACK is the other round, you're able to measure the internet side as well. So what this graph is showing is what's the round trip time to YouTube traffic, and you can see two things here. First thing is like there is a difference between wired host and wireless host, which is not surprising, right? Another good thing to really look into this graph, but what P4RTT can answer is that the internal leg, the in-campus RTT, meaning the host, campus host, to the switch, campus switch, where our vantage point is, that leg for the wireless is huge when talking to YouTube, right? So you can see like more than 50% of the RTT between YouTube and this host for the wireless it was actually from the in-campus RTT. Whereas the wired, like the majority of the RTT was coming from the internet side, which really gives us an idea how the wireless is working. Is it the bottleneck? Yes, sometimes it is the bottleneck. So with P4RT, we were able to answer these questions, which was very valuable for the IT folks as well. So summarize my talk. This talk was basically about jumping that research chasm, how to be less disruptive. And my advice was like, try to work on the passive monitoring and ask for a mirrored traffic tap, and then do the passive traffic monitoring first. How to preserve privacy is like always prepare your IRB applications really well. There could be more about that. And then try to use these anonymization tools, whether they're offline or you use our tool to do that, which is open for public. And how to actually do more collaboration with the research folks, having a joint position if possible. And then try to work on problems that matter for the IT as well. Because it's good for your research too, but it also builds a good relationship with your IT department. And I did share some real deployment successes, the OnTest tool, which you are using really well, P4OF, the real-time OS fingerprinting, and P4RTT, which is about continuous RTT monitoring. And there's a bunch of other apps we are working on, which is also very exciting as well. This talk, you can actually look into more if you want a long version of it. We did publish a paper in SICOM CCR called Experiment-Driven Research on Programmable Networks. So if you want to and have time, please feel free to look at that. It'll have more details of this talk and some other stuff, how to do research on real traffic and also using programmable data planes. For our group, basically Professor Jennifer Rexford group in Princeton, we also open up the P4 projects, the source code to public, both sometimes for the BMP2 version and also mostly also sometimes for the code that works for Tofino, because Intel and Barefoot allowed us to do that now. You can go to this GitHub repo to find the projects we have. So takeaway of this talk is basically, please join our effort. Like if you can do this, please try to do it because it's all good for us. This is how we can make an impact. This is how we can build some things that actually matter and work in the real world. So let's try to jump that research chasm together, going to real campus deployments. And we have more campus applications listed in our p4campus.cs.princeton.edu. I try to update that more often as well. And certainly there'll be more from you people on this call, and everyone has better ideas always. So this is a way to actually make an impact. And thank you. I'll take any questions as well now.
June, thank you very much for this talk. Very, very interesting. So if you have any question, feel free to write in the chat window or just unmute yourself.
Okay, is it possible to, so I think there's a chat saying, is it possible to expand the P4 campus to other universities such that external researchers can use live production traffic from Princeton when testing their P4 ideas? Very good question. This is kind of hard because for Princeton, other universities might be better. For Princeton, as I said, there's a pattern stuff going on. And for now, they never experienced, this is very new to them too, right? And pattern kind of says that, okay, they review your stuff and then, okay, you can use the anonymized traffic for your trace, but you have to list all the people who's going to have access to, and mostly they only limit it to the Princeton people, which is unfortunate. But I'm sure we are in talks with this, and there are some ideas actually how to share this. And I think Jack Russell, I don't know whether he had some ideas in Grant how to make this happen. And I'm sure if we work together, there's a way to, there's some process or way so that we can share our data, at least some sanitized version of it with the external researchers. and it's an effort. Like I think it'll be really good to do it, but for now we're working on it, I would say. Yeah. It's certainly possible that you give us, this happened, you give us our program, we will run it for you. And that assumes that, you know, we have a collaborating going on, and then we can share the data with you. And meaning that shared data probably is very aggregated. There's no way that you would know anything. So that kind of collaboration is possible, that you will give us a P4 program. That's a good thing about P4 programs, right? Like programs, like you give us a P4 program, we'll run it for you on the real traffic and share the results. And, you know, I'm thinking that we can make that decision, like probably I'll make that decision. This seems okay. I mean, this is fine, right? You know, because there's collaboration going on. That person is not looking at traffic I am, you know, so that will work. That certainly does work. All right. How hard was it to convince your CISO to tap into the enterprise network? So it was not that hard for us, right? Because as I said, we really utilized that joint position thing. When I was hired in Princeton, it was based on Professor Jennifer Redford grant and talked with the CISO, and they had a really good relationship. Let's hire June Kim, you know. So I already kind of started like that, and I know the CISO well. I know Jennifer Redford, and it was not that hard because I also worked for the IT department for a while. I built that trust with the staff and CISO, so it was not that hard. But if you don't have that, it may be hard. So that's why I did pitch that it may be a good idea to have that joint position. It kind of helps a lot. Thank you. Why is the internet activity much slower on your wired network than the wireless one? Tab location. Was that the case? I'm not sure. I think what you saw, let me try to go back there. Okay, here. Okay, so overall wired is much better, of course, than wireless. I think what you're saying is the red bar, on the red bar side, why is the red wired worse than wireless? Good point. I think it was just, I don't have a good explanation. I think it was just when we did the 90 percentile RTT, maybe it was not a long enough trace, but I thought it was no long enough trace, but there's a small difference, I guess, but I think it's not something substantial that needs explanations. But yeah, good point. But of course, the overall wired is much better than the wireless RTT. The internet side RTT is questionable. Why is that happening? But good catch. We may look into that more. All right. Where were the network taps you mentioned similar to something that like passive optical splitter? Yes, I think. So I'm not really. Okay, sorry, because there's. Oh yeah. I think that's basically it. I think they're more the same thing, right? They're, if you search for network taps, I think they're basically the same thing as passive optical splitters. Yeah. So they basically, yeah, they tap on the link and then like they're splitting out or mirroring. So that's basically the same thing as far as I know. Yeah. Yes. And Chris Tenji says yes. So that's right. Which switch model vendor did you use? I think this is for the P4 switch. We got it from EdgeCore, which had the Tofino chip on it. And the Tofino at that time was Barefoot, now it's Intel, right? So that's the switch we use. They have better versions, but I think in the research community, mostly they stick with EdgeCore switches, at least in the US. EdgeCore switches with Intel Tofino chips in it. And if you're in educational systems, I think still Intel has this research program. They used to call it FASTER program, where you can apply for and Intel would grant if you're doing research. And then they have this thing that you can join a forum where you can post questions, you can get access to their compiler, the SDK and all that stuff. Did you use the P4 switch as a packet broker? No, we did not. The packet broker system is totally different. I didn't get any money from there, but I'm just saying the truth that like Princeton uses big switch packet broker system, and now it's Arista, I think, and that's the packet broker system we use. It works well, but there's other packet broker systems, but we don't use the P4 switch as a packet broker. Cool, I think.
Right. Any other questions?
Jim.
Yeah.
When you mentioned that you are running your, let's say, your P4 campus as a part of, in a way to become some part of the production network, how much of these programs in P4 you are running right now is currently considered production?
I'm trying to think what's the definition of, do you mean like production level is not disrupting the network style?
Yeah, no, I understand that your infrastructure in P4 is somewhat plugged in the production network, and it's not in the path in the middle of the network. If it's down, it won't affect anything. But regarding the programs you are developing and using, is there any of the applications something that's the IT or engineering team is relying on for their work?
Oh, I see. Not now. Yeah. I guess partially they are relying on the anonymizer, right? But that's not for production actual traffic. Right now we are not running anything that they rely on or use every day. That would be awesome to do if we have a dedicated person and really good UI that shows that analysis or something like that. But for now we don't have anything that is used daily by the IT. But that's certainly our goal.
Sure. Yeah,
that would be awesome. Like if we had the time and people to really make this production level. But sometimes the research projects and graduate, it kind of stops. But it'll be really good if and you can think of like if the people think that's really useful, we can really make it production level at some point for some projects. Yeah.
Cool. Thank you.
Yep. Good question.
Right. I don't see any other question. Well, I want to thank you again, June. Very nice presentation, and in fact, the research group here at the USC benefit from the work from P4 campus, because we use the source code for certain projects. So thank you very much. And we'll be posting. Would you mind sending me the slides? So we'll be posting everything here on the website.
Cool. Do.
Thank you. Now continuing with our program, we will have a break. After the break, we will have a short presentation, 15 minutes. That will be about Tofino pods. One of the questions actually was, what are the switches that are being used in P4 campus? And this next talk will be about the pods that we have here at USC that use the same switches as those that are used in P4 campuses, edge core switches with Tofino chips. So we will be back in about 10 minutes, 2:45 p.m. Eastern time. After that, we'll have 2 hands-on sessions, and then we will conclude the workshop. So we're gonna be back in about 10 minutes, 2:45 Eastern time. Welcome back. And before we start the next presentation, there is a question in the chat window. Was Elika Fury question answer? And the question was, did you use a P4 switch as the packet broker? And the answer was, no, it was not a P4 switch, the one that is being used as packet broker. Now the next presentation, we will spend a few minutes, is a brief presentation about what we are doing here at University of South Carolina. One of the goals, the current project, the project that is being funded in this event from the National Science Foundation, is to do cyber training material. And that's what we're doing with the intro to P4 library, which use BMV2 switches. Now, internally at USC, we're also building a lab library that use the real Tofino chips. Hopefully, in a near future, this will be shared with the community. But it requires a little bit more of work with Intel. But we wanted to describe, and certainly we'll be happy to expand on this after the workshop. So this is a work that is being conducted by Eli and Jose. Eli and Jose are graduate assistants here at USC. So I want to give credit to them. And we're using this virtual platform, the platform that you have experienced when you go through the labs, the hands-on exercises. And we work closely with the network development group. This is one of the leading organizations in virtual training. So we use much of their features, their product called NetLab, and we use much of their features. So what we try to do, as you may have noticed when you go through the lab, we try to build high performance systems. Jose will show us today an example of running pods using the Tofino chips at 40 and 100 gig. The labs that we build shows functional realism. And what that means is that we use real IT hardware or the real code, for example, Linux code that you will use in a production network. We try to make it very easy for an inexperienced learner. So that's the presentation layer, making as easy as possible to navigate through the labs that we build. Also, the platform make it easy to create topologies for complex experiments. We will see today a topology that has multiple virtual machines and real hardware rather than just one single virtual machine. And we're attaching these devices, these physical devices, the Tofino chips, into the academic cloud, into the cloud system that we have here. The picture, how this looked like from our end. Well, when we run lab libraries, when we run an experiment, what had happened is a pod of equipment, for example, pod number 1, Tofino, or the BMB2, the orange, is created so you can run your experiment. And there are several hosts that are hosting these resources. In addition to that, there is one host. These are physical servers that is in charge of managing the whole system. The underlying hardware, CPU, RAM, storage, and Tofino switches based on Tofino chips. That's what we will see in a second. And we make this possible through these partnerships, as I mentioned before, the network development group, and also VMware, because we have here ESXi, running on the host, and vCenter, which is a product from VMware. So we are very grateful for these partnerships. Now, this presentation is about the pods that we're building using the real hardware. So we use these Tofino chips. More precisely, the vendor is EPSCore, and inside these switches we have the Tofino chips. And why do we do this? Well, first, because we want to streamline, make it as easy as possible our grad students and learners in general to learn this technology. And the idea of this platform is to have everything ready. We have to realize that these switches are white boxes. They come empty, and there is a considerable effort required to acquire, install, learn the operating system. We use an operating system that is called Open Network Linux. Acquire, install, and learn the compiler. This is from Intel. And if you need to acquire this, you have to sign an agreement with Intel, and then deploy the equipment, deploy the fibers connecting the switch or switches to the servers, configure the topologies. So all these items require considerable effort. So the idea of building this platform where everything is ready is that a learner who wants to learn, for example, a new student or a network engineer, has everything ready using the facilities that we're building here at USC. So Tofino pods help USC to onboard new students and researchers. That's our case here, so that they can immediately focus on learning how to program the switch. Additional to that, this is a shared environment. That means that the pod is reserved for 2-3 hours, whatever the time is needed to conduct an experiment. And then can be used by somebody else. So the pod is gonna be wiped out, clean, ready for the next reservation. For this pod, we use these switches from EdgeCore. The model is Wedge 100BF 32X. 32X because there are 32 ports, QSFP 28, and BF has a barefoot Tofino chip inside. And the programs are written in P416. At USC, we also take advantage of the Tofino model. This is a software switch that is provided by Intel that has very nice features for testing and troubleshooting. Specifically, the life cycle of a packet can be traced in the model, and that's not the case of the real switch. So this is the pod. What we do is we attach this pod to the cloud, and by logging in our cloud, making a reservation, this pod is deployed along with the lab manual, lab number 1, 2, 3, whatever is the exercise we want to execute, or if this is for research purpose. So there are some pods that are for research, are configured for our research purposes. How does the pod look like? First, the Tofino model running on a VM. The the hardware switch based on the Tofino chip. This is the EdgeCore. And then we have servers. The servers have a very good amount of memory. As far as I remember, is 256 gigabyte, but we will confirm that with Jose and Eli. They are the ones who are running this. And they have a dual port 100 gig Mellanox cards, which are also programmable, but we're not using that feature for now. We expect to do that in the future. all those lab exercises that you are doing as part of this workshop, similar exercises are available in this Tofino pod. Of course, we're porting the BMB2 code to the Tofino. And I want to switch right now to Jose and Eli, who are the two leading persons that are building these lab libraries. Jose, do you want to share, or Eli, do you want to share your screen?
Yeah, sure, I can share that.
Or as you prefer, I can do also the demo if you want, but
that's fine, whatever you prefer.
okay, I will let you lead from here.
Okay. All right, so here in this slide, we're gonna show how the platform looks like. So this is like a short video. So basically, this is the topology. We have our servers, and we have a software switch. This is the Tofino model, and we have the hardware switch. And the motivation was to have these two in the same topology. Is that the Tofino model will be basically used for debugging and when you first start writing your P4 program, because it gives you the ability to see how the packet is traversing the pipeline. And then if you want to do like a test where you have high performance, for example, 40 gig or 100 gig, all you have to do is just shift to the other switch, which is the hardware. So the PCs here are Linux machines. They are running Linux, and the Tofino model is as well in a VM, a Linux VM. We tried to do the development environment similar to what we did with the BMV2. All we have to do is just set that we want the environment to be ASIC or model. And if you select ASIC, we have an SSH connection to the hardware, and this is where we're gonna be running all the commands there. For example, here we are running the switch daemon, and we are specifying the program name. And then, of course, you can turn on the ports that you would like. Here we are turning 2 ports, 100 gig. And of course, many of these can be automated. So it depends on what is the purpose of the application you're trying to do here. And then here is where you see your P4 code. You can, of course, modify it, do any kind of programming there. And currently, at this point, we are just populating the match action table with some entries so that we have some forwarding. So you can see like everything is in one interface for editing and compiling and then deploying to the switch. And here we are just testing the connectivity, and this is going through the hardware. So we are going through the Tofino switch here. So we've seen that we have successful connectivity with ping. And here at this point, we are trying to see if we want to use iPerf to generate large traffic. So we want to see if we have a certain application generating a large amount of traffic, if we can forward those using the P4 switch, and potentially if you are doing some in-network application that requires high traffic rates. So this would be a very interesting thing to do. As you can see here with this iPerf test, we are reaching around 50 gigabits per second. So here we just want to make it clear that the bottleneck here is in the senders. So there is some fine tuning that you can do on the senders, specifically with the NICs. And once you do that, you should be able to get up to 100 gig.
Yeah, and again, the nice thing about this at least my experience with my students is that this attaching the devices to the cloud and building this pod is that even my students' intro to computer networks can do P4 in a real hardware with very limited knowledge. But the key is that everything is up and running, is ready. Otherwise, there is a learning curve that they have to follow. So hopefully the idea of this short presentation is we hope that we will have a workshop running the real hardware pretty soon. That's the goal with my colleague, Jason Suraski, and my group here at USC. I don't know if there is any question about this. Okay, there are no questions. There is one question from Jeremy. You mentioned programming NICs. Are those the Bluefield 2? Jeremy, if I understand well, Bluefield 2 is a model of NICs. Would you mind clarifying that? But what I was saying is that the physical pods, the servers have programmable NICs. We are not using yet that feature. We expect to do it in a future. Okay, and with that, we will start our first hands-on session. This hands-on session is session number 3, hands-on session number 3. We will talk about match action tables and how to use exact matching, longest prefix match. So this session will be conducted by Eli, but you have access, all of you have access to the pod. So feel free to log into the platform, and if you want to follow with Eli, you are welcome to do so. So Eli, do you want to start? And just to clarify, which lab is this in the lab set?
So this is gonna be lab number 6, which is called Introduction to Match Action Tables, part 2. And we decided part 2 because it contains some part from part 1, and I think it's gonna be more comprehensive. So yeah, that's the lab. All right. So in this hands-on session, we will start by describing what are those match action tables, why do we need them when we deal with P4, and then we're gonna see how we can implement them on BMV2 and test whether they are working or not. So in this slide here, we can see back the architecture that we discussed last time, and this is related to the V1 model, but basically any architecture that is related to programmable data plane use as main component the match action tables. And those match action tables are defined within the programmable match action pipelines, so in the ingress and the egress. This is where we're going to implement the tables, the actions, and we will start by invoking those tables or applying those tables. Now, in a table, we can actually implement any kind of logic. So we can use it to implement some traditional switch tables for routing or flow lookup, ACL purposes. Or what is more important, especially for P4, is the ability to do customized user-defined complex logic, right? So in the previous presentation, we were seeing some very nice applications. Many of those applications are leveraging tables and these match action units inside the switch so that they perform their goal. So how does a match action table operate? We can see here we have in the match action table, we have a key, we have an action ID and action data. And basically, by default, those tables are empty and we need to populate them with some entries, right? And usually this is the job of the control plane to populate them. Okay. And then what we need to do is we need to get some fields from the headers and the metadata to construct a key. And this key will be used for lookup in our table. Now, once we have, we can have here two kind of scenarios. The key is there in the table, so we will have a hit. And if it's not there, we're gonna have a miss. So if we have a hit, then the action that is in that specific record will be executed, and the action data will be passed to that as well, right? And you can see here, we have some action and it has a code, and we will be able to know whether we have hit or not, and therefore we can know what to execute in that action. So we know the action ID, so the name of that action, and the parameters of that action. Now, in case we have a miss, so the key is not found in our table, then we're gonna be using the default action. And the table, when you define the table in a P4 program, you can specify what the default action is. And like in any other action, there's some action data that you can also pass to it. Okay, I can give here a very simple example. If you wanna achieve IPv4 forwarding, there's plenty of ways you can do that. And this is completely decided by you as the programmer. But if you want to walk through this kind of example, in the match action table, let's say we called it IPv4 forwarding table. We use the control plane to populate it with some entries. For example, here the key is destination IP, so 192.168.0.1. And then for the actions, we have one action which is called IP forward. And the action data would be what egress port on the switch to use whenever we have a hit on that destination IP. And then the key that we want to construct, we will extract it from the packet headers, destination IP. So after we do the parsing for, let's say, IPv4, there we can now extract this destination IP. And we do a matching. We can see here that we have an entry, so we have a hit. And therefore, the IP forward action will be executed, and the action data EG_port = 4 will be passed to it as well. Now, what is this action doing? This is also defined by you as a programmer. In our case here, we are doing something like just setting the egress port of the traffic manager. So we are telling the switch where to forward this packet from. And we are here also decrementing the time to live. But again, this is not the only way to do it. So you can decide what to do there. And in this lab that we're gonna go over now, we have this topology. So there's one P4 switch, a BMV2 switch, and 3 hosts, H1, H2, and H3. We will be implementing 2 tables. One table will use the longest prefix match, or LPM. And in this kind of matching, we basically match, as an example, we can match on a whole network rather than on just a single IP address. But it can be used for other matching besides matching on IPs. And then the other table would be to use the exact matching. So we will try to match on exactly the IP address rather than a whole network. And once we have a match, we will assign the output port, and then we will also update the MAC addresses in the headers and decrement the TTL. All right. So now I will go to the platform where we start doing the hands-on. So we are still using the same platform as we did last time. All you have to do is log in using your credentials. And once you are there, you have to just select lab number 6. So it's lab 6, introduction to match action tables, part 2. All right. So now we are inside the pod. We can see here we have one client, and the manual is located here in the content. So we can just display it. What I usually do, I undock this, put it aside. So I will put this on the left-hand side, and then the platform on the right-hand side. Okay. And So like the other labs, we will start first with some generic information about the lab. What is the objective, an overview about the topic discussed. There's a table for the credentials that the devices that you have in your topology might use. So for example, here, the password is password all small caps. You will see that we will use that while we are doing the lab. And then we will start by describing what is the objective of this lab, some little theory about what to expect in the hands-on later on. For example, here we are talking about the LPM, the longest prefix matching, and we are showing how a typical code looks like. But I will skip those and just go over the hands-on because we will be describing them as we type the code. So starting from section 2, this is where the hands-on starts. We will be using Mininet for emulating this whole network, and the switch that we will use is a BMV2 switch. So I will first click on my client here to enter to the VM, and then I will start Mini-Edit, which is the graphical topology editor for Mininet, and it's asking me for a password. The password is password all small caps. And now we are inside Mini-Edit. So we already built this topology so that we don't have to rebuild everything here for every lab. And you can find the topology file by clicking all file open and then specifying the lab number. In our case, we are doing lab 6. And then we select lab6.mn. So now that we have loaded the topology, the next step is to start the emulation, and we do so by clicking on the run button. And now that those buttons are great, so it means that our topology has started and we are ready to go inside the host, perform any kind of command there, as well as on the switch terminal. So now we will see how we can get into one of the hosts. So for example, if I want to go to the terminal of host H1, all I have to do is right click on H1 and hold the right click. And then I will have to click on terminal. And here it's showing me the terminal of host H1. So I can issue here any command that you usually use on Linux. For example, ifconfig. So I'm here in step 2. I want to see the interfaces that I have on host H1. And we can see we have one interface, H1-ETH0. This is the IP address, 10.0.0.1/8. And we have a loopback interface. All right. So now in section number 3, we'll start by defining the table in our P4 program. Before we do so, we first have to start our environment, and we will go to the terminal icon, which is on the desktop. And from there, we will type in code P4 labs, and then lab 6. This is to start the Visual Studio Code and use the lab 6 as the main folder. And what you can see here is, as we did last time, so we have different files for each part of the pipeline. So we have the main file is basic. So this is where we are invoking the switch instance. And then we have a parser. You can see it's already implemented. And we have the ingress block, egress, we have the parser, checksum, and so on. And as we were talking, whenever we implement those tables, we can implement them in the those ingress processing block or egress processing block. For now, we're just gonna be using the ingress. And now I click on ingress.p4 to see the content of this file. We can see that we have a control called myIngress, and we have all the right parameters there, but it's still empty. So nothing has been implemented yet. And this is what we're gonna start by doing now. So we're gonna implement these tables that perform forwarding, right? But before we implement the tables, we have to list and define what are the actions that will be used by those tables. So for instance, I will start with one action which is called forward, right? And to do so, you have to type in action and then the action name. So here you can call it whatever you want. We are just calling it forward. And then you can pass on parameters to this function. So these to this action. So these are the action data that we were discussing in the slides. What we are doing here, we are passing the destination MAC and the output port. Okay, now those types here are defined in the headers and we discussed them last time. So this is how you can have type def and create your own type, right? But you can always say bit 48 instead of MAC address underscore T. So MAC address underscore T, DST address. Then we have egress spec underscore T port. And now we start by defining what is this action doing. So it's very similar to how we define a regular function. And so what is happening here is that we are setting the output port, which is part of the standard metadata. And metadata, if you recall, these are just the, this is some data that passes through the pipeline. And we have some standard metadata that contains some predefined fields that you would use for processing the packet. For example, if you want to set the output port, there is a predefined field called egress spec, right? And so what we are doing here, we are setting this predefined output port, which is part of the standard metadata, to be equal to port, which is whatever was sent from the control plane, right? This is the parameter here. So standard metadata dot egress underscore spec is equal to port. So again, I'm just passing, I'm just assigning the output port based on the value of this parameter, which we usually populate from the data, from the control plane, sorry. Next, we are doing here some swapping for the MAC addresses. So what we are saying is we want to modify the source address inside the Ethernet header. So here we are doing header modification to be equal to whatever destination address was already in the headers. So I'm assigning the previous destination address as a new source address in the headers. And this is showing you here how P4 can be used to apply packet header modification. In this case, we are changing the value of the source address to be equal to the previous destination address that was inside the headers. And if you want to change, for example, part of the IPv4, all you have to do is write hdr.ipv4. Whatever field that you are planning to modify. Okay, so hdr.ethernet.source address is equal to hdr.ethernet.destination address. And I just wanna say that those fields here that we are typing them, this is what we did last time, right? So you can see all of those in the headers, right? This is where I'm getting those names here. And if you define this as, let's say, DST underscore ADDR, then you have to use that later on in your table definition. Okay. And now we are assigning also the parameter from the control plane, pass from the control plane, which is the destination address or the MAC, to be equal to the new destination address. So hdr.ethernet.dst address equal to st address. And also what we are doing here, we are decrementing the time to live. You can see here, so this is just an example to show you that you can use some basic expressions in P4. For example, you are subtracting here 1. So hdr.ipv4.ttl is equal to the previous value of the TTL minus 1. And basically, that's it for the action. So now we just created an action called forward that accepts the destination MAC and the output port as parameters, and we'll do some processing. In our case, we are changing the output port of the traffic manager, and we are changing some fields inside the headers. Next, we will define another action, which is called drop. And the idea here is just to drop the packet, right? Whenever this action is being invoked. So I will also type in action. We will call it drop. So this is what we define it, right? The name of the action drop. You can obviously change the name to whatever you want. Now here, there is a predefined in the V1 model, something called mark to drop. And basically, it accepts the standard metadata here as parameters. And what it does is really is that it's just setting the output port to be the dropping port. Okay. But so far we defined those two actions, the forward and the drop, but we didn't create the table yet, or we didn't say that these two actions belong to a table. And basically this is what we have to do next. So now we will create a table, which we will call IPv4 exact, because in this table we will be using exact matching. So table, and then you give it a certain name, whatever you want to call it. Here we are calling it IPv4 underscore exact. Now, in the table, we have to define what is the key, right, for that table. So what are we trying to match on? So we type in key equals to, and here we start by listing the fields that we want to match on. So for example, what we are doing here, we are saying we want to match on the destination address, which is part of the IPv4 header. And we want this match to be exact. So this is what we mean by exact matching. It means that we're gonna try to match exactly the same value as whatever is inside the header. We are not doing an LPM where we can try to match an IP from a certain network. So now we defined what is the key for this table. Next, we have to list what are the actions associated with this table. So actions, and we're gonna list the two actions that we created, right? So we have forward and we have drop. These are the two actions that we will use in our IPv4 exact table. We can also specify what is the size of this table. So how many entries do we want to store in that table? And obviously here you can't like select any number, you can make it very large. It depends on how much resources you have when we talk about real hardware. For here in this example, we are just using 1024. And we will specify a default action. So again, the default action will be invoked whenever there is a miss. So we don't find this key inside our table. So our default action here would be to drop the packet. So invoking the action drop. Okay. So this is what we have to do when we create a table. We have to create the actions that you are planning to use in the table. You have to specify the key, the lookup key. You have to specify what are the actions associated for that table, the size, and what is the default action in case you have a miss, or in other words, in case your key was not found in the table. Now, what we're gonna do is we're gonna create another table, and this table will be doing longest prefix matching instead of exact matching. So now I'm in step number 5 here, and basically we are calling this table IPv4 underscore LPM. So table IPv4 underscore LPM. And then the key is also the destination address from the IPv4 header. So HDR IPv4.dst address. But now instead of using exact for the match type, we're gonna use longest prefix match or LPM. Regarding the actions, we are gonna be using the same actions that we used for the previous table. These are forward and drop. Okay. Now, obviously, you can create other actions and have some actions for one table, other actions for a different table. But here, because both of these tables have the same purpose, which is forwarding based on the destination address, we just use the same actions in both tables. Okay. Now, same thing for the size. So size is 1024, and the default action is drop. Okay. Now, after creating the tables and listing all the actions that are associated with these tables, if you just keep it like that, nothing will happen. And the reason is every one of those control block, right? For example, my ingress, it needs to have the apply in it, this apply block. And basically what you can think of it as this block will start executing with whatever is inside the apply. And everything else before was just definitions. So they are not executed yet. So we have to write here apply. Now I'm in step 6. And basically here is where you can start by deciding what is the logic, which table you apply. If you want to have some if statements, you want to do some complex code later on, this is where you would actually do it, right? And so what we are doing here is we are creating an if statement, a condition, just to check if the IPv4 header is valid. And by IPv4 is valid, here we mean, did we parse IPv4 when the packet was received? If the parser actually parsed IPv4, then there's an implicit flag bit that is set to valid. And therefore, this condition here will evaluate to true. Now, let's say you received an IPv6 packet, then your parser didn't parse the IPv4, and therefore this condition here will evaluate to false. Okay? So if header dot IPv4 dot is valid, so now at this point we know that our IPv4 was parsed, so we have an IPv4 header. We can start by applying the tables that we defined. So what we're gonna do is we're gonna say something like, let us start first with the exact matching table. If it is applied, then fine, it's enough. If not, then we will apply the LPM table, the longest prefix match. And to do so, we can also type here another condition. So if IPv4 underscore exact, so that's the table name, I'm applying it now, so dot apply, and then dot miss. So I'm checking here if we applied this table and we have a miss, so that there's no entry inside that table for this specific destination address. What we can do is we can now try to apply the other table, the IPv4 LPM. Okay. And it's really important to understand that when you look at some ingress block, let's say you are trying to read some other code, it's always a good idea to start reading from the apply. So this is where you know the sequence of how those tables are invoked or any kind of processing that you do inside the data plane. So at this point, we know that we are checking for the validity of IPv4, and we are, if it is valid, we are applying the exact. If we have a miss, then we go to the LPM and apply it. Okay. And of course, at the end, we want to make sure to save. So just by using Control S or file save. And this is important. Otherwise, when you compile, you got to be using the empty version of this control block. So now step number 4, we will compile. This should compile successfully if we don't have like a typo. So p4c.basic, remember that we compiled the main file here that is calling the pipeline. And so it compiled successfully. There is no error that's being returned. And we have a basic.json file generated, which we will be using to actually define what is the data plane is. So this is the binary that you would usually use on a hardware. This is the output of the compilation. And therefore, because this is the output of our compiler, we need to push it to our switch S1. So now push to switch. We're going to specify the file to push. In our case, this is basic.json. And then the switch name, which is S1. Here we are asked for a password, and the password is again password all small caps. Next, we will verify that the file is in our switch. So we will go back to mini edit. And then we will go inside the terminal of the P4 switch to see if the file is there in the file system. So right click now on the S1 terminal. And there I will issue an ls command. And we can see we have our basic.json. It was pushed. So this is the one that we just compiled now, the output of our compiler. And then we want to make sure to understand what are the ports being used by the switch, so that whenever we start the daemon, we tell it that use this port as port 0, this port as port 1, and so on. So before we do that, we can see the interfaces that are available on our switch, ifconfig. And what we can see is we have basically the loopback. There is one interface for, this is for management, so we're going to skip that. But most importantly, we have S1 ETH0, S1 ETH1, and S1 ETH2. And basically, those are the interfaces that are connected to the host H1, H2, and H3. So these are the interfaces that you see here. Next, we will start the switch daemon. And we do so by using the simple switch command, which we see here. So simple switch -i. So port 0 on our switch will correspond to interface S1-ETH0. And then again, -i, port 1 is for S1-ETH1. Then -i2 for S1-ETH2. And we also supply here the nanolog parameter just to be able to see the logs inside the switch. And this file here is like, we just specified it. You can specify any other file basically for IPC. Now, most importantly, when you start the switch, you have to give it the output of your compiler. This is your definition of the data plane, which is the JSON file, right? And this is basic.json. And we also started in the background because we're gonna do some more commands in the same terminal. It's telling us that it added successfully the interfaces and assigned them to those port numbers that we specified when we started the switch. Next, I will press enter here to return to the CLI. And then I will use this command here to populate the tables that we just created. So simple switch CLI. And we have a file that contains the rules or those table entries. We already created those. It's inside this folder, lab6, and it's called rules.cmd. And basically, I'm just getting it as input to this command here, simple switch CLI, which will insert those entries in the data plane. And now that we know a little bit about tables, we can see what is happening here. First, we can see that an entry was added to an LPM match table, which is called myingress.ipv4 LPM. And notice how it's using the control block first in the and the name of that table. So it's saying that we have a table IPv4_LPM, which is inside the block my ingress. The match key for this specific entry is first it's of type LPM and is A000/8. This means that if you change from hex to decimal, this is 10.0.0.0/8, which corresponds really to the network here on the left-hand side. And our action, so whenever we have a match here, we will execute the action, which is my ingress.forward. And the runtime data, so remember we had two parameters in the action. We had the destination MAC and we have the output port. And this is what we are seeing here. So this is destination MAC and this is the output port. Okay, and this entry that was added has a handle 0. So later on we will see that when you navigate this tool, you'll be able to delete a certain entry by its handle and so on. Now we have another entry also for the same table, but this time the match key is 14, and this corresponds to 20.0.0/8. This is the IP address. And it has some also other action data, right? So this is the MAC and this is the output port. Now for the third entry, we can see here we are now adding one to the exact table, which is my ingress.ipv4_exact. And here the match key is also exact and 1E, which is 30.0.0.1. And notice here how we are using exactly the IP address rather than using a whole network as we did in the previous two entries. And whenever we have a match, we call the forward action and we pass with these two parameters. Okay, now in the second part, now the next session, we're gonna navigate this CLI so that we can see how we do all this table population manually. Basically what we are doing here, but we're gonna see how we can do it from scratch. Okay. Here, when you go through the lab, there's some explanation. Then we will start this nano message client just to be able to see the logs inside the switch. And now on host H2, we will start Python script that will sniff on a certain interface, H2_ETH0. So to do so, we have to go to the mininet, right click on H2 and then terminal. And from there, just run this Python script here. Then we will go back to the terminal of host H1 and send the IPv4 packet here to 20.0.0.1. So I have already host H1 terminal opened. I will just maximize it. And then type in send.py to the destination IP 20.0.0.1. Hello world. And basically here we can see that this is how the packet looks like. These are the headers. So we have Ethernet. On top of that, we have IP and we have TCP. And now we can see the logs of the switch to make sure that our tables were really used, right? So I will go to the behavioral model. This is the terminal for the switch. We start here by looking at the packet in. So a packet was received on port 0. The parser was executed, and we can see that we parsed Ethernet and IPv4, and then the parser ended here. So we parsed the IPv4. Next, we start with the ingress block. So this is pipeline start ingress. And here we see that there is a condition evaluation, and it's telling us that it evaluated true. And if we go back to the code, we are talking about this condition here, which is whether IPv4 is valid or not. In our case, because we parsed IPv4, then this validity bit was set to 1, and therefore our IPv4 is valid. Okay. And then we have a table being executed, which is IPv4 exact, but we have a miss. We don't have an entry for that. And this is because we didn't inserted this entry in our exact table. And so the default action would be executed, which is drop. However, whenever we have a miss, if we go to the logic here, when we have a miss, we will start by executing now or applying the LPM table, right? And this is what we are seeing here. So next we have the IPv4 LPM table, but now we have a hit, and that's because we inserted this entry from the control plane.
Eli, can I interrupt you, because there is a question that is exactly about this.
Sure.
The question is, if there is a miss with the LPM table as well, would there be an implicit drop?
It's basically what you write in the default action, right? You can have it as a drop so that you drop it. I believe if you don't write anything, like if you just keep it without this default action, then nothing will happen. So I think it might be an implicit drop, but I'm not sure. We can check that really.
Now in your code, line number 39 is clear, default action is drop. So there is a drop. That's what you are referring to. There is going to be a drop.
Exactly. Yeah.
Thank you.
Sure. Now, so again, we were talking about this LPM table. We have a hit, and therefore there is an action that was executed. So the action that we executed was my ingress.forward. And this is basically this action here, right? And we executed this action, the pipeline is done. Next, remember in the architecture, we have an ingress and an egress pipeline. So we start with the egress, but the egress is empty. And you can confirm here that we have nothing in our egress, right? And then after that, we have the deparser, the checksum update, and we have the deparser to emit the table. And we can see at the end that the packet was transmitted out of port number 1. Okay. So imagine like you have a more complex application that involves other kind of header modification. All you have to do is define those actions, decide what you want to do there, and then create the tables. And you have to make sure to populate the tables from the control plane, and you will be able to have this custom packet processing. Now, I want to mention that what you write here inside the action, when we deal with software switches such as BMV2, it's very flexible because we don't have the limitations of the hardware. But when you start developing applications for the hardware, here you might have some limitations, specifically if you have a lot of data dependencies. So you have to wait for the output of one instruction to use it as input for the second, and so on. And you'll be limited by how many stages you have in your certain hardware switch. Okay, and that's where all the innovation comes in. You have to try to fit this program, which is not like a super easy task to do. It requires a lot of understanding of the hardware to be able to do it. For the software switch, we don't have this issue, so you can keep writing here, and it's gonna compile without any problems. So next here we are sending another packet, but this time for 30.0.0.1. This is also from host H1. So use the up arrow and then use 30 here. And if we go back now to the logs of the switch, basically we have to look at where the packet in is. So this is where actually this packet started at this point. Again, we have the parser executing at parsing IPv4. And then we have the condition, this condition evaluated to true, but now we have a hit on the IPv4 exact, right? And we have a hit, so we execute the forward action, and that's it. So we don't go for the LPM. If we had a miss like we had in the previous step, then we go to the LPM table. And basically that's it for this labs. If there's any question, Dr. Jorge, I can take them.
Eli, thank you very much. There is a question in the chat window. So the action execute drop, the action drop after the first match table is not actually executed?
Yeah, that's a very good question. It is executed, but really this this action, when we talk about like this mark to drop, all this is doing is set the port to what they call the dropping port, right? But because later on we rechange this port to the actual egress port that we specify here, then you are overwriting it and it's not dropping the packet.
All right, thank you. Let's see if there's any other questions. There's no other question. Eli, briefly, do you want to just share with us your how important is this having the logs? Because you clearly follow the logs, and if you have the real hardware, you don't have this log. But fortunately, Intel has this Tofino model. So do you want to briefly describe your experience with the logs and how important it is?
Yeah, sure. So here at the University of South Carolina, we developed so far like a few before applications. Initially, I started with BMV2, and then we went over the training and we went over the Tofino part. And when we developed those applications, like if you just try to implement it immediately on the hardware, it can be really, really tricky because there's a lot of things that you might think it's gonna work, especially if you are used to the regular programming, not the type of programming that you use for those ASICs. You might think it will work, but it actually doesn't. So you have to see the logs. For Tofino, there's the Tofino model. The nice thing about it is that it gives you more verbosity than even this BMV2 log, right? So there you can really see exactly what is happening. When you have, let's say, a hashing on some fields, you can see exactly what the hash value is. If you are using stateful elements, you can go really in detail and see exactly what is happening. So with the hardware, it's always a good idea. Start with the model, see the logs, make sure you are creating your program correctly, try to do a lot of testing. Typically, they use unit testing and the packet test framework, PTF, for more verification of the program. And then once you are sure, okay, it works well, all you have to do is just get the output of your compiler and then deploy it on the hardware. And basically, this is what we are doing with the pod that Dr. Jorge was showing. We just test on the model, we get the output, we deploy it there, and we run. So we don't even have to recompile on the hardware. It's exactly the same code. And then you'll be able to see in high performance, whatever your results are.
Thank you, Ali. There is another question. How many match action steps does this example use?
So it depends on how many tables you are using. And there are some other elements that might use match action as well. But for now, we have two tables. So we are using the IPv4 and exact and the IPv4 LPM. And we try to do two matches here, one on the exact destination address and one on the LPM for destination address. And I think this is a good question when you deal with the hardware a lot, because there's a lot of what they call those action units and packet header vector, hash units. There's a lot of hardware ALUs. You will be able in the hardware to see exactly which one of those are being activated, are being used. Now for the model, it doesn't make a lot of sense to use or to get them. It's nice to know them because you know how complex your program is. But typically this is like the kind of question that you go and see what the hardware is doing. And with that, we know with Intel, because we work with those switches, with the compiler, once you compile, it will produce some graphs and logs, and you go there and you inspect them, and it will tell you exactly how many hardware or how many units in this specific hardware you are using. So you know if you are consuming more stages, you know what is the SRAM and the TCAM and so on and so forth.
Right. So basically, that's something that BMV2 does not provide. But if you were really compiling with the P4 compiler for Intel, the compiler will be placing the tables in different stages and will show you how many stages you are using.
That's correct. Yeah, and they have like graphical interface, like a web-based interface where you can see exactly the stages and how much you are consuming. So it's really nice because when you build complex and network applications, as Dr. Khay was saying, their compiler is smart so that it tries to place the tables correctly, right? But also it gives they give you the option to specify if you want to do everything manually and try to bypass those kind of things that are related to compiler optimization, right? But then it would require more understanding of the underlying hardware.
I don't see any other questions. So thank you, Ali. And we will continue with the last session of the workshop. We will have a break. Let's come back at 4 p.m. in 9 minutes, and we will have a hands-on session on populating this match action table from the control plane. That's what Ali will be doing in the next session. So we'll come back in 9 minutes. All right, we're back for the last session of this workshop. The hands-on session number 4 is about populating and managing match action tables at runtime. Eli will be leading this session. So Eli, I will let you share your screen.
All right. So in this session, we're gonna see how we can populate those match action tables. And this is happening at runtime. It means that we compile the program, we deploy that program on the switch, and then at runtime, we decide what are the table entries that we want to insert in those tables. We talked a little bit about it in the previous presentation. Whenever we have a match action table and it has the match key and the action data, they come empty by default. So you create a table that has no entries at all. And it's the job of the control plane to decide what are those entries that will be filled here in the table. And the control plane has more than just inserting the entries. So you can remove, you can update, and you can even configure some elements in the P4 switch that are also related to other advanced topics such as multicasting and other stuff as well. But here we are saying that we are just seeing how we can insert a certain entry in the table. And basically, when we do so, we have to specify which table we want to insert the entry to, because remember that potentially you might have multiple tables in your program. And then for that table, you want to specify the action and the match key value. So for example, here we are saying for IP forwarding, IP4 forwarding table. So that's the table name. For the action, IP forward. And the key here is 192.168.0.1. And then the action parameter here, which is 4, right? And this corresponds to the action data, the egress port. Now, for the BMV2 switch, which is using the simple switch target, there's a tool called simple switch CLI that we use to populate the tables here in this lab series. And this tool includes a program independent CLI. And this means that the available functions to be used inside this command line interface are not depending on what you write in the program. For example, if you have something like table add, it's just accept the table name as part of its parameters, right? So, but it's not like table add and your table name all within one function. This is what we mean here by the program independence. And if you look at this diagram here, we see that in the data plane at the bottom, we have simple switch, which is the target of BMV2. And in that switch, we have a program independent control server. So there's a server that is running there. And then from the control plane side, we have the same thing, but it's a client. And this client will connect to the control server and basically call these APIs to manipulate the tables. Now, the connection between these two is through Thrift here, which is based on TCP sockets. And there are other ways to actually have this control plane, data plane communication. For example, you might have heard of something called P4 runtime, for example. But here we are just sticking to the most simple way, which is through like this Thrift communication. And we are assuming that we are doing things locally on the switch. So the switch will have the data plane and we will use the control plane on that same switch. So for this lab, we're going to be using the same topology as the one that we used in the previous one. So one switch and 3 hosts. So for this lab, there won't be any P4 programming. So we will assume that the P4 code is already written, right? All we have to do is just compile it, push it to the switch, and from there navigate this tool, which is used to populate the tables at runtime. But we will not do any P4 programming. And we will see some features such as displaying the ports, tables, actions, and how we can insert, update, and remove the table entries. Okay, so I will shift now to the platform. I already made the reservation, so this is lab number 7. Okay, it's called populating and managing match action tables at runtime. All right, so we're gonna be doing the same thing as we did, same structure for the lab, right? I'll start with the theory. Here in this specific lab, we are discussing how the runtime works. So what is Thrift, gRPC, those kind of protocols that are used for the communication between the control plane and the data plane. Okay, and we are emphasizing that we're gonna be using the simple switch CLI to manage those tables at runtime. So from section 2, we will start first by opening mini edit, which we will find a shortcut on the desktop. And there we're gonna type in password as the password. So again, we're gonna be using the pre-built topology. This is gonna be the one related to lab 7. So all we have to do is file, open lab 7 and lab7.mn. So now we have the topology here. The next step is to, of course, run that topology by clicking on the run button. So before we proceed, I just wanna re-emphasize that you are free to build any topology that you want. So you can potentially have multiple P4 switches. For this lab series, we just started very slowly, very basic. We are just using one switch, but you might wanna, let's say later on, if you're exploring advanced topics and you wanna see how subsequent switches are modifying the packet, you can just click and drag at those switches. And another point here is that beside the P4 switches, you can drag legacy switches. And also you can use routers which run FRR. So you can really deploy a complex topology here for research and basically try to experiment with it. And one other point is that this whole VM, you can find it on the website under the resources table. So if you want to deploy it on your machine, you can just download it from there and use it on VMware or VirtualBox or any virtualization software. All right, so let's continue now. Second step is to go inside the terminal of host H1. So right click on H1 terminal and then verify the interface configuration. Want to make sure that there's some IP addresses there and the interface name, as we did in the previous lab. So we have this H1, H0, and we have the IP address. And note here how also the way we develop those labs is that for the MAC address, we use the convention of all zeros followed by the host number. So here, this is zeros followed by 1, and then for H2 is going to be zeros, 2, and so on and so forth. All right, now we're gonna start first by going to the programming environment, compile, and then push this program. But we're not modify the program. It's already there. It's already written for us. So let's start by launching the Linux terminal from the desktop here. And then type in code P4 labs, and then lab 7. Okay, so now we started the Visual Studio Code, and we can see here we already have a program. The basic is already calling all the pipeline. We're instantiating this main here. And if we go to ingress, we can see that there's already some implementation written here. And also for the parser, it's already there. So all we have to do is just basically compile this program. P4C, basic.p4. And we have here a basic.json, right? That's the output of the compiler. Next step, as usual, once we compile, we have to push that output of the compiler, which defines the data plane, to our switch. So basic.json S1. And the password, again, is password here. Okay. Now, we can verify the configuration that this specific file was pushed to the switch. We have to go to mini edit, right? And then go inside the terminal of the P4 switch. Right click and then terminal. Then confirm that the file is there. So ls, we have basic.json. And then, as usual, we want to make sure that the interfaces are there. So we type in ifconfig. And as you can see, we have those 3 interfaces. And the next step is to start the daemon. And so far, what we were doing, I'm going a little bit fast on them because that's exactly what we did in the previous lab. So we just compiled, push, and now starting the daemon. Simple switch -i 0 at s1-eth0 -i1 at s1-eth1 and 2 at s1-eth2. We're gonna enable logging. And then give the input, which is the compiled data plane here, basic.json, and run it in the background by using the and character. Now we're gonna start by looking at the simple switch CLI. First, I will press enter just to get the terminal back. And now instead of calling this tool and sending as its input some file that was already created, we assume that we're gonna do everything from scratch inside the tool. So what we're gonna do is we're gonna start by typing in the tool name, which is simple switch_CLI. And because we are running it locally inside our switch S1, so it automatically detected that we have a switch daemon that is running, and it connected there. It obtained the JSON, which defines this data plane. And now we can basically issue the runtime commands so that we manipulate the tables at runtime. Okay, now there are some parameters that you can supply for this command, especially if you decide to have this control plane to be centralized, like in a controller, an SDN. But then all you have to do is give the port number that's, that the switch is listening on. And this way you can basically manage multiple switches as well. Okay. Now, the first thing we're gonna do, which is super helpful, is just type in the question mark here. And this is gonna show us the available commands. So there's some commands here that you can see for action profiles. First, you have counters. Those are some stateful elements that you would use in a P4 program. You have some multicasting you can modify here. But most importantly, at least for now, we have the table commands. So we have table add. This is for adding an entry. We have table clear, delete, dump, and many other commands that you can use to manipulate that table. Okay. Another thing we have to mention here is that we talked a little bit, we've seen multicast and other stuff. This tool allows you, or basically any runtime tool allows you to do a configuration for the traffic manager. And this was the non-programmable element, which was in the middle of the pipeline, right? So for example, creating multicast groups or doing some complex stuff like setting the queue size, all of these are done here in this tool, right? For example, set queue depth, set queue rate, and so on. So for now, we're just gonna be looking at the table commands so that we know maybe a few other commands, but we're gonna be focusing mostly on tables and not on the other objects. Also, I should mention that tab here is super important. It will allow you to autocomplete. And you can always get a help for a given command by typing in help followed by the command name. So for example, I want to see the syntax of the table dump. I can type in help table dump. And this is going to tell me that this command will display the entries in a match table. And the syntax is table dump followed by the table name. Okay. You can do also, so you can issue some commands to display information about the ports. So for instance, if we type in show underscore ports, it will tell us that port 0 on your switch is mapped to S18H0, port 1 to S18H1, port 2 to S18H2. They are all up, so we know that they are up and running. And you can see here that this is exactly what we decided when we started the simple switch target. We said that 0 at S18H0 and 1 is at S18H1 and so on. Okay, so here you can see all the interfaces and ports and make sure they are up. Next, you can also see what are the available tables in your program. And this is important because let me first just enlarge a little bit this window so that we try to show as much as possible in one line. Show tables is important because a lot of times you have like a complex program that has a lot of tables. You might be using a program someone else did, and you want to see what are the available tables here. So, if you don't want to go over the code and open each and every file and try to trace what is happening, it's just easy to just use show tables. It will tell you that we have IPv4 host, part of the my ingress block. We have IPv4 LPM, part of also my ingress block. This is what we created in the previous lab. And it's gonna tell us some more information. So you can see here MK, this is the match key, is IPv4.destination address. And the first one, the IPv4 host, uses exact matching, and the LPM uses the LPM matching. Okay. You can also see the available actions. So show actions. There's an underscore between them. And you can see we have two actions. We have a drop action in my ingress. It doesn't have any parameter. And we have the forward action, which is also inside my egress, but this one has destination address, which is 48 bits. And we have the port number, which is 9 bits. This is the port on the switch, right? Port 1, port 2, port 3, and so And also, you can display some information about the switch as a whole. So you can say switch info, and this is gonna tell us that this device has an ID of 0. The Thrift port that's used is 9090. So this is useful if you wanna connect to multiple devices running on the same machine, so you know what are their ports. And you will see here some more information, which we will not go through, but basically these are related for logging and notifications. Specifically, this file we've seen when we started the simple switch target, right? There's a lot to explore in this tool. It depends on how detail you want to keep digging in it, right? We are just covering the basics, at least to help you get started by using P4. There's also a nice command here, which is called get time elapsed. And this is going to tell you for how long the switch has been running, right? And this is showing you the time in microseconds. So yeah, so we have here micro, milli, and then you have here the seconds. This is how long the switch has been up. And by up here, we mean when we started the simple switch target. All right, so those are the generic ones. Now we're gonna see how we can actually go into details regarding tables and manipulate the entries there. So the first step here is to display some information about the tables. For example, we can use the command table info if you want to get information on a specific table. So table underscore info, and you give it the table name. It's very important here, try as much as possible to use the tab. This way you avoid any typos. And basically you can see here, I typed in, or I pressed on tab, it showed me my ingress.ipv4 underscore. And the reason is both of my tables start with IPv4 underscore. So if I press tab again, it's gonna show me you have host and you have LPM. So let's say host. And this is gonna give me information about the specific table. You can also show the actions that are only for this table rather than showing all the action as we did before. So this is gonna be here in step number 2. Table, show actions, and then you give it the table name. In our case here, my ingress.ipv4 host. Okay. Now, this one is very useful when you want to see what are the available entries inside the table. You want to display everything inside it. You want to dump the table entries. And the command to do this is table underscore dump. And also you give it the table name, right? So at this point, you can see that table entries, there's nothing. And it's showing us that we have a default entry, which is the drop, right? So it's only telling us that we have one default entry. There's no entries. If you have entries, you would see them under this table entries header here. And sometimes it's useful when you have large tables, you want to make sure that, let's say you have a plenty of rules that you pushed and you want to make sure that all of them are there. You don't want to go over each of them one by one. You can just display how many entries you have in your table so far. So if you type in table underscore num entries and then the table name, it's going to tell us here at this point we have 0 entries. We didn't push anything yet to it. Okay. Now we're gonna move to how we can add entries. So there is a command called table add. If you want to see how it looks like, what is the syntax? So we're just gonna use help, then table underscore add. And this is telling us that this command is used to add entry to a match table. The syntax is as follows. So table add, then you start with the table name, space, you have the action name and the match fields, right? Now here you would see there is like a equal greater than sign, which is like an arrow. Basically, this is used to separate whatever you have before for the match fields and the action parameters. Okay, and optionally you can provide a priority, but we will not go over that in this lab. Now we'll see an example how we are actually adding an entry, and you'll see how it's mapped to this syntax definition that we see here. Okay, so let us try to add an entry to the IPv4 host table. So we'll start by, so now I'm in step number 2 here. So we'll start with table underscore add, and then we give it the table name. Remember to always write the whole name. It means that including the block where this table is. So in our case, it's in my ingress. So my ingress.ipv4 host, that's the table name. So all of this here correspond to the table name in the syntax. And then we have the action name. So we want to forward traffic for a given, let's say, IP address. So I will say that whenever we have a match on this IP that I'm going to write in this command, I want to execute the forward action. And also for the actions, we have to specify the whole name, including the control block name. So my ingress.forward. This is for the action name. Next, we have the match fields. So what is the value that I want to add to my table, which is going to be the key on our table, right? We know that we are matching on the destination IP. That's what we did in the previous lab. So here we have to type in some IP address. And remember, we are working with the host table. It means that this is an exact matching. So I can't write here /24 or /8 or anything like that. I will just write the IP address exactly as it is. So here we are saying we are adding an entry for the IP address 30.0.0.1. So these are the match fields. Now, once we have a match, right, and we executed this action, which is forward, what are the parameters that I want to pass to this action? And I will just move very quickly to the P4 code, just so that you understand what we're doing here. In the ingress.p4, this is where we are creating the table and the actions, right? And in this command here, we are saying that we are adding to IPv4 host, right? So it means that for this table, okay, specifically for the action forward, right? And the match key, which this IPv4 host here is 30.0.0.1. Now, if we have a match here and the forward is executed, we want to pass some parameters. And those that you see here, the set of 0, 3, and then 2, these are what you pass here as parameter to the action. So first we have the MAC address. This is it, 0000000000 and 03. And then for the port number, this is gonna be 2. If you had here more parameters, then you can keep writing here what parameters that you want. Okay, so always read it in a way that you are adding for this specific value for the key. And once you have a match, you want to execute this specific action. And for this action, you are specifying these parameters. All right, so let's go back and finish this command. So I'm gonna write here 00 4. Okay. And by the way, you can just write 3, but here just to make it easy to understand what we are doing, we are typing in the whole thing, right? And then, so this is for destination address, and then for the port, this is gonna be port number 2. And once we press on enter, you can see that we got an output similar to the one that I was describing in the previous lab. So essentially, in the file that we've been populating our tables with in the previous labs, all they contain is a sequence of table add commands such as this one, right? So if you put these in a file, you can pass a batch of these commands, all of them to the simple switch CLI, and therefore all of them will be executed and the entries will be inserted to your table. Okay. Now that we added one entry, we can reissue the table dump and see if it recognized that there's a new entry there. So table dump, and then my ingress.ipv4 host. And you can see that now we have an entry 0. The match key is destination address, exact, and this is actually the value that we added, which is 30.0.0.1, but it's represented here in hex. And for the action to be executed, it's forward, and the parameters are 0.3. So this is like a summarized version of what we wrote here, and then 0.2 for the port number. Okay. And now if we go back and also type in the previous command that we used, the table num entries, my ingress.ipv4 host, you can verify that it's incremented by 1. Now, we can also display a certain entry by using is match key. And this is very, very important because sometimes you have a lot of entries in a table and you want to see if a specific key exists there. So you can do so. You can type in this step 5 command here. So table dump entry from key. The table name, so my ingress.ipv4 host, and then the IP address or the key that you are using. Here in our case, this is, and you have to type it here in hexadecimal, right? So 1E00001 means the IP address 30001. And it's telling us that there is an entry for this key. Its number is 0, and this is the action to be executed for this key and the parameters for this action. Also, you can dump an entry by using the entry handle, which is these zeros that we've been seeing here. And this is like just a counter that starts from 0 and keep incrementing when you add more and more entries, right? So if you know that a certain entry in your table has this specific entry number, you can also display information by using that number. And the way to do it is just table dump entry, the table name, and then you give it the entry handle. Here it's 0. And it's going to show us the same output, basically showing this match key, right? Also, it's important, especially if you are creating some logic on the control plane and you are modifying some entries in the data plane, you might want to modify sometimes some entry that's already there. And you can do so by using the table_modify. So table_modify, we can always type in help table modify to see the syntax. But it's super easy. It's very similar to the one that we used before, the table add. So you start with table modify, and then you write the table name. So my ingress.ipv4 host, and then the action. And here you have 0. This 0 here represents the handle. So this is the number that we were using in the previous command, right? So we're saying that we want to modify the entry numbered 0, and now the new action parameters would be 0, 0, 0, 0, 0, 0, 0, 0, and 0, 5, right? So remember it was 0, 3 before. The port was 0, 2. Now we're gonna put it to 5. So modifying entry 0 for this exact match table. And then we can reissue the same command to make sure. So I'll use the up arrow. And you can see that now for this specific entry, the action parameters are 5 and 5, basically what we wrote here. Okay. So this is how you can add and manipulate an entry for an exact table. So how can we do it for an LPM table? It's also super easy. All we have to do is first specify the table name that's LPM, And then when we write the key, we have to specify / followed by a number, right? Typically, this would represent like a network. So for example, 20.0.0.0/8. All you have to do is write that here when you use the table add command. So let us try this now. Table add, my ingress, but now it's not IPv4 host, it's IPv4 LPM, because we are using the one with LPM matching. And then we will use the forward action. The match here would be 20.0.0.0/8. So this is the part here that is new. We are adding an address, and we are using the /8 to represent that this is the LPM key. And the action parameters, as usual, we use this arrow here to separate them. 0, 0, 0, and then 0, 0, and then 0, 2. And our output port would be 1. Okay, you can see now that the match key is showing that it's LPM, right? And this is for the IPv4 LPM table. Okay, and again, here we are seeing this 1.4. This is because it's in hex, but if you convert it to decimal, this should be 20, right? And then you can always delete a table entry. So you have a certain entry there, you want to delete it. So table delete my ingress dot IPv4_LPM. So we are specifying which table we want to delete the entry from. And then we specify the entry handle. Again, this is the index here for this entry, right? So we have 0. So we are removing this specific entry from our table. Another also very useful command is to clear a table. Sometimes you have a lot of entries there, and you just want to reset everything and start from scratch. So you can use table clear. This is going to remove all the entries from the table. So this is now here in step number 3. So table underscore clear, and you give it as a parameter here the table name, so IPv4 underscore LPM. And then we can verify by using the table num entries, and then the table name, which is IPv4 LPM. And we can see now it's 0 because we cleared that table. So this is a short lab that contains the basic commands that you would use for manipulating those match action tables. So as we discussed before, if you use the question mark, there's much more. We didn't cover the advanced parts because we didn't discuss yet what is multicast or counter or register and those stuff. We just saw the important ones that we use with tables, at least just to be able to populate the table and make sure that you have some entries that the data plane will use as the packet enters to your switch. But obviously there's a lot to explore here, and hopefully in the upcoming lab series we're gonna discuss like the advanced part of what you can do in the data plane, and there we're gonna show both what you would write in the data plane program and then how you can use this tool for handling whatever advanced feature that you use in the data plane. That's it, Dr. Jorge, if there's questions.
Yeah, thank you, Lee. There are 2 questions. The first one is, have you considered adding tabs to the mini edit to test things like what it was discussed by June?
Mm-hmm. So there's here like there's a challenge here if we want to talk about tapping. We know that the switches, the software switches, they have the port mirroring, or they have a duplication of packets from one port to another, but these are not good for applications, for example, that are in network, because you would lose some timing information and you will get packet reordering and other stuff as well. Tapping, it might not be entirely possible here, and the reason is you might be able to do it, but then you would create kind of like a like a dummy interface in the middle and try to do that manually. I haven't done that before. I don't know if it's possible. I'm not sure if it's possible, but tapping in an emulated environment, especially with BMV2, for example, won't make too much sense because the timing information that you get from the switch is not granular. So it might be useful a little bit for like initial tests, but if you are planning to do something that really leverages the power of those programmable switches, you want to go to the hardware for timing measurements. Here you can always have like TCP dump and redirect the traffic to, you know, maybe some other interface. That is possible. But tap that will preserve the packets as they are, I haven't tried that. And again, I don't think that doing that on a software switch will be very, very relevant because of the timing information that is lost.
The second question is port number 5 just for an example? I don't see a port 5 on the labs before switch. So you use a port 5, yes.
Yeah, definitely. That's just like an example for the modify. Basically, it will accept it. It's not gonna complain about it. But here we have only in the topology here we have 3 ports, 0, 1, and 2. This tool didn't complain if you use a value of a port because it doesn't know exactly that this is a port, right? For this tool, this is just like a value that is 9 bits, and that's why it is it's just accepting it. But yeah, does it make sense in our example because there's no port 5? That's definitely true.
A new question. Is there a command to duplicate packet without being multicast?
So there might be, I can check here. There is something called mirroring that you can configure. And basically you would use that, all of this from the control plane. And this means that you're gonna be mirroring packet from one port to another. Now, if you're talking about duplicating packets from the data plane, this is like a whole different concept. There's what they call cloning and recirculation, but those are a little bit advanced. We didn't touch upon in this lab series. And you have always multicast here to create the groups and to associate nodes with the groups as well.
Right, let's see if there's any other questions.
There's one comment I can add as well, since we have some time. So what we are doing now is using the simple switch CLI, right? And this is communicating with the target through Thrift so that you issue all these commands. But it's always possible to have your own, for example, Python program. If you decide you wanna make an application on the control plane that is dynamically maybe pushing those entries or updating entries, you can create a Python program, and from there you can import the library. There's like few things you can write in the Python program. You will instantiate an object, you will connect to the Thrift server, and there you can basically issue any of these commands that we are seeing here programmatically from a program. This way you can automate things if you are interested in doing so.
There is a question or a comment from Chris. Eli, I don't know if you prefer to read. It's a long one, or I can read for you.
Yeah, I can see it now. So in the output of help table add, it shows match fields, arrow, action parameters. I can see how the action parameters map onto the IPv4 action forward args. Can you explain how it knows that match fields is a destination IP versus some other thing that you want? Yeah, that's a very good question. The way this tool knows, this is what happens. So I will exit from it and then run it again. What you can see is it's saying that it's obtaining the JSON from the switch. And this JSON basically is, your data plane. And if you try to open that file, which is basic JSON, you will see that it contains all the necessary information. I think one of those information is the names that you are using there, right? And so this is how, when you use the auto-completion, for instance, in that tool, it knows exactly what are those names are, okay? Yeah, you can explore here, but basically this is like a whole representation of your data plane. So the more complex your P4 program is, the larger this file is, and you will see more information about what you wrote here. But this is specific to BMV2. I have to mention that. We know, for example, with Intel Tofino, the output is not JSON, right? And it's proprietary, so it's like .bin. It's a binary output. So you can't actually see any of those. But there you also have like some APIs that you can use to manipulate the tables. All I'm saying is for this tool, it's taking this JSON because that's how the data plane is expressed when you compile for a BMV2 target. Yeah, no problem.
All right. I don't see any additional question. Well, thank you very much, Ali, for this last session. And this was the last session of this workshop. So I want to remind everyone, first, I want to thank you all for coming to this workshop. All the material that was used in this workshop will be in this website, including the video. For example, the recording of day number 1 is in the website. The day number 2 is going to be within the next 1 or 2 days. It's going to be here, including the PowerPoint slide of the presentation that we had today. In closing, Jason, I don't know if you want to add anything.
Nothing to add, just that this has been a really great workshop, and we hope that everybody was able to get some good experience in learning about P4 and related technologies. And the team at University of South Carolina is an excellent resource if anybody does have questions in the future, or if anybody does want to spin up some of the training instances to pass these lessons on to anybody else at your campus that may benefit from it. Not only for the P4 topics, but for other cyber infrastructure topics as well. And we will be announcing another workshop pretty soon in April that's going to be focusing on other CI engineering things. And we will make sure to announce via the same channels that we did for this workshop.
Right, thank you, Jason. To conclude, I want to, again, I said this at the beginning, and we will be organizing additional workshops also on P4, the continuation of what we presented here. So we use intro to P4, so we will be building more advanced material, and we will be disseminating this. Finally, I want to ask you to please take a few minutes. You will be receiving an email with the survey. Your input, the feedback is very important to us. It helps us improve the workshop. You will be receiving that email tomorrow. So I want to thank you all again. Thank you for the interest on this workshop, and have a good rest of the day.